mysterious traveller has slipped into our cosmic neighbourhood. Astronomers call it 3-Eye Atlas, and the latest analyses suggest its trajectory is shifting in subtle but meaningful ways. Is this just normal physics, or a clue that this interstellar visitor is stranger than we thought? Let's dive in. Imagine meeting a traveller who doesn't share our sun as a home address, an object forged under another star's light, carrying the chemistry and scars of a place we will never visit. That's what astronomers mean when they talk about 3-Eye Atlas. It isn't a planet, and it isn't one of the familiar comets that loop around on repeat visits. It is an interstellar passerby, a piece of elsewhere, crossing our skies just once, and only for a brief moment in cosmic time. The day it was noticed, it didn't look like much, just a faint moving point among 10,000 others. But the motion told a different story. Instead of tracing a lazy ellipse that says "see you next century," its path sketches a hyperbola, the mathematical signature of a guest that won't be staying for dinner. That one curve already hints at everything that makes 3-Eye Atlas so valuable. It arrives from beyond, reminds us how big space really is, and then it keeps going, daring us to learn as much as we can before it fades. The first thing astronomers do with an odd mover is check the arc, how its position shifts night to night against the star field. With just a handful of measurements you can guess an orbit, but with dozens you can start ruling things out. If the orbit wants to close back on itself, it's ours. If it refuses to close, taking on that open-armed hyperbola, it belongs to the galaxy at large. For 3-Eye Atlas, the solutions quickly leaned interstellar. The numbers that matter are simple in spirit: an eccentricity greater than 1, a speed that stays stubbornly fast even far from the sun, and a direction on the sky that doesn't match the usual comet highways shaped by our planets. None of that requires exotic physics. It's just gravity speaking plainly. This object fell toward the sun, swung by, and is marching back to the dark, on a path that never was and never will be bound. And yet, just gravity undersells the drama here. Every interstellar object is a time capsule from a different planetary nursery. Our own comets remember the dusty edge of the solar system, the era when ice and rock were sticking together into larger and larger seeds. 3-Eye Atlas remembers someone else's beginning. Perhaps it formed beside a red dwarf where stellar flares bake one side of every pebble. Perhaps it was born amid the heavy element richness of a star a few billion years older than ours. Perhaps it's a shard from a world that never quite made it. That memory is written, faintly, into its light. When you disperse that light into a spectrum, like smearing a fingerprint, you might glimpse water vapour, carbon-bearing molecules, sodium, or just the subtle colour slope of dust grains that are coarser or finer than those we know. Even a non-detection teaches us something. Silence is still a clue about what is, or isn't, boiling off the surface. The name itself points to the chase. Atlas marks the vigilant survey telescopes sweeping the sky for anything new, bright or dim, tame or surprising. As those robotic eyes flagged a mover, the global relay began. Observatories in different longitudes and latitudes checked in, stacked exposures, refined positions, and cut the error bars down to size. Amateur astronomers joined in too, because the sky does not care about your funding level when you have a clear night and a calibrated camera. Together, those timestamps build a story frame by frame, a flipbook in which 3-Eye Atlas glides past familiar constellations, while the numbers underneath grow sharper. Once the orbit looked convincingly interstellar, attention shifted to behaviour. Is there a coma, a fuzzy shroud of gas and dust, swelling around the nucleus? Is there a tail, straight or curved, pushed by sunlight or magnetised winds? Sometimes the answers are ambiguous, because distance and faintness smear the picture. But even a barely there haze can matter. If 3-Eye Atlas is venting, the escaping gases act like tiny thrusters, providing non-gravitational nudges that make its course deviate from the pure trajectory textbooks draw. Those nudges are not noise to be subtracted. They are signals of activity, telling us about volatile ices, the microstructure of the surface, and the way heat penetrates and radiates back out. The same sunlight that lets us see the object can slowly reshape its path. The stakes are high because we've had so few chances. With Oumuamua, the first recorded interstellar visitor, we faced a paradox. It was bright enough to see that something odd was happening, but too fleeting and small to pin down its nature. With Borisov the second, the universe was gentler. It behaved like a classic comet, easing the analysis. 3i Atlas becomes the third lantern on the path, a chance to say which features repeat and which were unique quirks. Do interstellar wanderers tend to be crumbly and active, or hard and quiet? Do they redden with space weathering in a similar way? Do their rotations settle into predictable patterns, or do they tumble, making thrusts asymmetric and wobbly? Every new measurement chips away at ignorance. Calling it rare is not hype. The galaxy likely ejects uncountable shards during planet formation, and the solar system must be ploughing through that slow drizzle all the time, but only the tiniest fraction are big and bright enough to catch with our current surveys, and fewer still pass close enough for rich follow-up. That scarcity turns 3i Atlas into a communal project. Infrared observatories can search for the warmth of dust. Large optical telescopes can stretch faint spectra into legible lines. Radio dishes can hunt for larger grains or unusual molecules. Even tiny space telescopes can watch its brightness rise and fall to infer a spin period. Each instrument adds a layer, and layered together they sketch something like a personality. Meet the Visitor isn't just a tagline. It's an instruction to slow down and notice the basics well. What is its absolute brightness once you correct for distance and solar phase? Does its light curve hint at a stretched cigar-like body, a flattish shard, or a cluster of fragments moving as one? Are there sudden outbursts that spike its brightness, suggesting fragile crusts that crack as sunlight digs deeper? How does its colour change with phase angle? Does it look redder when seen at a shallow angle, a clue about surface roughness or dust? These are not arcane details. They're the bones of the biography we're trying to write before the subject leaves the room. Beneath the technical talk runs a simple human current. Curiosity pressed against a deadline. Nights are short, weather is fickle, and 3i Atlas is both faint and fast. You schedule time, clouds roll in. You get a clear night, the moon glows fat and drowns the faintest features. So you squeeze signal from noise, stack images, subtract the sky, and coax meaning from the few photons that do arrive. It is meticulous, patient work. Thousands of small choices that together determine whether we can later say, with confidence, what this traveller is and isn't. There's also a quiet humility in meeting something that doesn't belong to us. We have named most things in our solar system and learned their tempos. 3i Atlas obeys different ancestries and accidents. Perhaps it was peeled off a growing world by a close encounter with a giant planet, flung into exile long before our species learned to grind lenses. Perhaps its surface carries minerals that haven't been common here since the first billion years of the sun's life. It is easy to romanticize, but the facts are romantic enough. Light from another sun poured onto this object for eons. Starlight from ours will touch it only once. And so, meet the Visitor really means pay attention now. Attend to the curve it draws in space and the whisper of gases, if any, that trail behind it. Attend to its spun-out rhythm, its shy colour, its reluctance or willingness to shed dust. Attend because 3i Atlas will reward attention with answers we cannot get any other way. When it recedes, dim, then invisible, the numbers we've gathered will be all we have left, a ledger of what we learned from a messenger that came uninvited, lingered briefly, and showed us that even in a sky we think we know, there are still letters arriving from other addresses. The night it began looked ordinary. The sky patterned with thousands of quiet points and a few soft smears from distant galaxies. Yet inside the survey's computers, a set of near-identical images were already being subtracted from crisp reference templates. Difference imaging is a simple idea with sharp teeth. Take tonight's picture, subtract last month's clean sky, and whatever changes pops out. Supernova, satellites, noise, and every so often a faint thing that moves in a straight line from frame to frame. The pipeline measured point spread functions, fit centroids, and binned detections by how convincingly they rose above the background. Most candidates die right there. Hot pixels, cosmic rays, glints from planes or satellites. The software has seen every trick. But this one refused to die. In exposure A, it sat barely 5 sigma above the noise. In exposure B, it nudged a bit brighter. In exposure C, it shifted just enough that the algorithm could stitch the three together into a tracklet, a tiny arrow in the sky with a rate and a direction. The system chimed its first alert. Real bogus classifiers, trained on millions of past detections, gave the candidate a high probability of being real. Cross-matching removed known asteroids, catalogued comets, and near-Earth objects with similar rates. The position didn't land on any known minor planet ephemeris. The proper motion was fast but not absurd. The brightness was steady enough to be trustworthy. A human stepped in then, because someone always has to. They pulled up the thumbnails, blinked them between exposures, checked for trailing that would betray a satellite, checked the angle relative to the ecliptic where most solar system traffic cruises. Clean. The coordinates and a rough magnitude went to the confirmation feed. A few minutes later, the second observatory in the network, thousands of kilometers away, caught the same mover with the same skyplane velocity. 2 eyes make a line, 3 eyes make a story. That was the moment people started calling it, half-joking, 3-eye atlas. Follow-up is a race against the geometry. With only a short arc, a handful of measurements across an hour, you can fit many orbits and none will be happy. Extend the arc to a night, then 2, and a single family of solutions starts to win. The first night's astrometry landed in the queue at the data center, where the orbit solvers took over. They ingested the right ascension and declination, the timestamps down to fractions of a second, the uncertainties derived from the fit to the local star field, calibrated against Gaia so the coordinates were pinned to a solid grid. The code explored ellipses, parabolas, and finally hyperbolas, weighting by how small the residuals were between predicted and measured positions. The residuals shrank when the curve opened up. Eccentricity edged past 1 and refused to come back. Meanwhile, telescopes you've never heard of, and a few you have, swiveled on cue. Some tracked the stars and accepted a short trailing streak from the object. Others guided non-sidereally, letting the stars smear into lines while the target held still, a neat reversal that squeezes more signal from scarce photons. Photometry teams measured the flux in fixed apertures and then in PSF matched apertures to look for a halo larger than the seeing disk. A coma would mean outgassing. A clean, star-like profile might hint at a colder, quieter surface. Early results were maddeningly in between. A profile barely bloated beyond the stars on some frames, indistinguishable on others. That ambiguity kept everyone honest, and kept the request for more time rolling in. The Minor Planet Center's confirmation page lit up with observers volunteering windows from every longitude. Europe picked it up at dusk, then a desert observatory in the Americas carried the baton through midnight, and farther west the Pacific Rim stretched the arc to dawn. Parallax between sites slightly nudged the apparent path. Fold that into the solver and the distance estimate sharpened. With better distance comes a better speed. With a better speed, the orbit classifies itself. The hyperbolic fit now wasn't just allowed, it was preferred. People whispered the word interstellar, but refused to write it until the numbers were bulletproof. If you've never watched an orbit converge, imagine tightening a knot with many loose ends. Each new point pulls the solution a little, sometimes too far. A new reduction of the same old image can loosen it again, because someone found a catalogued star with a bad colour term and corrected the plate solution. Seeing matters. A night with fat, unstable seeing introduces astrometric jitter that inflates uncertainties. A night of clean, cold air turns the same telescope into a scalpel. In the chat threads, you'd see notes like FWHM 1.2 inches tonight, residuals drop to 0.2 inches RMS, or moonlight elevated background, switching to red filter to squeeze SNR. None of that reads like romance, but it's where the truth hides. Pre-covery searches began even before the orbit settled. Teams combed through the past few weeks of survey images, stacking at the predicted rate of motion, track and stack, to dig the object out of the noise where a single exposure would miss it. 2 pre-coveries surfaced from nights before the discovery, faint marginal dots that lined up with the current best-fit hyperbola. Those points did more than extend the arc. They pulled the speed estimate away from the solar system's comfortable norms. Even far from the sun, where gravity's tug is weak, 3-eye Atlas ran hot, still fast enough that when extrapolated backward, nothing you could do with planets and time would wrap it into a bound path. At the same time, the discipline of killing false positives never let go. Airplane strobes can mimic a moving dot if you catch only one burst per exposure. Starlink trains can sneak through with short trails that masquerade as points under poor seeing. Sensor electronics can cough up repeating noise in exactly the wrong part of the chip. The team rotated cameras, dithered pointing, changed filters, and verified that the centroid moved exactly as the sky predicted. not as a fixed detector artifact would. Consistency across instruments is the cure for self-deception. Photometry began to add personality. As the phase angle changed, the Sun-object-Earth geometry, the brightness curve didn't behave like a pure, inert rock. It fell off with distance a touch slower than expected, as if a faint dust shroud were reflecting extra sunlight. Spectroscopists booked time and dispersed the meagre light into a low-resolution spectrum, hunting for the broad, shallow features of dust and the narrow lines of simple gases. Most nights the spectrum whispered more than it spoke, but even whispers help. A red slope points towards space-weathered organics. A flatter spectrum suggests fresher ice or larger grains. 3I Atlas didn't look exotic, but it didn't look exactly like home either. Inside the orbit-fitting code, a tiny, non-gravitational parameter toggled from off to on. Early, it stayed set to 0. Prudence dictates that you don't add free parameters until the data demand them. As more astrometry poured in, and the fit stubbornly preferred a slight outward push near perihelion, modelers tried a conservative term, the simplest way to represent gentle cometary thrust without overfitting. The chi-squared nudged down. Not a revelation, not proof of jets, but enough to justify more watches near sunrise and sunset when thermal contrasts on the surface might be livelier. The sociology of discovery unfolded alongside the math. Graduate students took shifts at 3 a.m, writing quick-look reports and pushing reduced measurements before heading to class. Amateur observers posted gorgeous, deep stacks that professional pipelines envied, because a single well-tuned backyard rig can stare for hours, where a large facility must hop from target to target. Senior astronomers played air traffic control, deconflicting overlap and making sure the sky got covered across latitudes so the object wouldn't slip between daylight gaps. Journals remained quiet. Whiteboards and private notes did the talking, while people reproduced each other's results and tried to break them. Night by night, the uncertainties shrank. The covariance ellipses on tomorrow's predicted position tightened enough that smaller telescopes could find it efficiently. Acquired became the most satisfying word in the logs, followed closely by linked, when a new set of detections attached neatly to last night's solution. 3I Atlas had stopped being a rumour and become a trackable thing with a calculable future, and that future did not loop back toward the sun. It dipped in, past an invisible gate where bound comets turn, and then angled out again, free. Not ours, and never had been. If the first pings were all about detection, the next were about intention. Which instruments would sprint for early spectra, knowing the object would brighten but also change? Who would monitor the light curve nightly to catch rotation, and maybe tumbling, that could explain any later course deviations? Who would attempt radar, ambitious for something so faint but not impossible with a well-timed window? Even the naming logistics started quietly in the background because names trail certainty. The mood was careful, almost ceremonial, numbers first, claims later. Yet in the quiet excitement that crackled through emails and midnight coffee, everyone felt the same thing. The universe had nudged the bell and the ring had reached every screen. A new traveller was here. 3I Atlas had entered the ledger not as a rumour or a glitch, but as a line of coordinates that pointed to the wider galaxy and said plainly, look. When astronomers say that the path of 3I Atlas is shifting, they don't mean it's whipping around or making dramatic turns like a car on a mountain road. They mean something quieter and more precise. The predicted path, based only on gravity, isn't matching the measured path by a tiny but persistent amount. Imagine you've drawn a clean pencil line across a page and then start laying transparent sheets over it, each with a dot where the traveller actually appears that night. If the dots all sit right on the pencil line, gravity alone tells the whole story. If the dots creep a hair above the line one night, a hair below on another, you might suspect a measurement noise. But when the dots drift in one preferred direction over many nights, inch by inch, you have a real effect. That gentle drift is the shift. The baseline expectation is simple. The sun's pull sets the course. Planets tug a little when the visitor passes their neighbourhoods, but for an object like 3I Atlas, the sun dominates. From that, astronomers calculate a path that's smooth and predictable. Then they line up the human reality against the mathematical ideal. Telescopes log the position down to fractions of an arc-second, and the clock time down to fractions of a second. Those positions are compared to the prediction. The tiny differences, the residuals, are supposed to scatter randomly if everything is behaving. If instead the residuals lean in a consistent direction, night after night, that's the telltale sign. The orbit isn't wrong, it's incomplete. Something besides gravity is nudging. What could nudge a small world wandering near the sun? The most common culprit is outgassing. As sunlight warms the surface, ices buried in pores and cracks can turn to vapour and escape. The gas drags dust with it, and together they form a jet. A jet acts like a microscopic thruster. You won't see a dramatic plume, you'll see its consequence. The object's speed and path change a little in the direction opposite the jet. If 3i Atlas is spinning, those jets may switch on and off as different patches face the sun, giving the nudge a rhythm. Picture a sprinkler head clicking as it turns. Each click is small, but over time the lawn gets wet in a pattern. Sunlight itself has a say. It carries momentum. When countless photons hit and scatter from a surface, they exert a push so tiny you'd laugh if you could feel it in your hand. Over millions of kilometers, that laughable push adds up. There's also the warmth the object re-radiates after absorbing sunlight. If one side heats more and cools more efficiently, the thermal glow can create a steady, gentle thrust. None of these effects are exotic. They're the quiet housekeeping of space. Light pushes, heat sighs, ice breathes. The shift is simply those whispers becoming audible in the data. Detecting a real shift and not fooling yourself is its own discipline. Telescopes judge position by comparing the visitor to background stars with perfectly known coordinates. Those stars come from exquisitely precise catalogues. If you pick the wrong stars, or the atmosphere blurs the image, or the camera has a tiny distortion you didn't correct, the dots on your transparent sheets move in fake ways. That's why teams obsess over calibration. They measure the shape of the starlight, correct for slight colour differences, map the camera's quirks, and recheck the timestamps. Then they ask other telescopes to try. When multiple instruments, using different cameras and different nights, agree on the same drift, the case hardens. The shift passes from rumour to result. Once a shift is real, modelers upgrade the orbit. They keep gravity, of course, but they allow for a small additional push that aligns with the sun or with the object's motion. They don't guess wildly. They choose the simplest form that explains the data without overcomplicating the story. If the fit improves and keeps improving as new measurements arrive, that's a sign they're on the right track. If it improves for a night and then falls apart, back to the drawing board. The philosophy's conservative. Add only what the sky demands. For a voiceover audience, here's a gut-level way to feel the scale. Imagine a ship crossing a calm sea, steered by a steady engine. That's gravity. Now imagine a breeze that is so light you barely notice it on your skin, but it always comes from the same side. Over hours, the ship lands a little off the plotted course. The captain didn't turn the wheel, the breeze did. With 3i Atlas, the breeze is sunlight and sublimating ice, and the off-course landing is what astronomers see as that slow, steady drift in position. The timing of the shift matters. These nudges tend to grow as the object approaches the sun and weaken as it recedes. Heat wakes up shallow pockets of volatile material. After a while, those pockets empty and go quiet until the next warm-up. That natural rise and fall becomes a signature. If observers see the drift increasing as the distance to the sun decreases, and then easing after closest approach, it points strongly to outgassing or thermal effects rather than to some one-time measurement mistake. Rotation and shape turn the situation from simple to interesting. If 3i Atlas were a perfect sphere with a uniform crust and a gentle spin, the jets, if any, would average out in a very tidy way. Real objects are lumpy, with ridges and pits, and they can tumble rather than spin neatly. A jet coming from a crater on the morning side will push differently than a jet from a flatter afternoon plane. Over several rotations, the push averages to a preferred direction, but the average can change as seasons change on the object, or as dormant regions start to vent. That evolving average is another flavour of shifting, not just a constant nudge, but a nudge whose character changes with time. Light itself carries clues about this dance. If a faint coma forms, a thin halo of dust and gas around the nucleus, its shape will often lean away from the sun. Subtle changes in the brightness curve can hint at when a jet turns on. By watching the light rise and fall over hours and days, astronomers can estimate a rotation period. If the timing of those brightness wiggles lines up with changes in the measured drift, you begin to connect cause and effect. The object spins, a vent faces the sun, The path shifts a smidge more during those hours. It's like hearing footsteps and seeing a door move at the same time. There's also the practical side, navigation. Even a tiny shift left unmodelled will ruin predictions over weeks. If a telescope points to where 3i Atlas should be based on gravity alone, it may miss the target entirely when the actual position has wandered a little each night. By embracing the shift and folding it into the orbit, observatories keep the visitor in their sights. The reward is compounding. Better predictions bring more data refine the shift. The refined shift improves tomorrow's predictions. It's a virtuous loop. It's tempting for big headlines to spin shift into something ominous or miraculous. But the truth is more satisfying because it's real. These small forces are part of the standard toolkit for understanding small bodies. We've seen them on comets born in our own deep freeze and on asteroids that slowly drift between resonances over years. With 3i Atlas, what's special isn't the existence of the shift. It's what the shift reveals about a traveller from a different star system. The amount of push hints at how much ice hides under the crust. The direction hints at where the active zones live. The way the push changes with time hints at texture, layering, and even the depth of the warmed surface. You can think of it as reading an invisible map with your fingertips. Each night's position is a raised dot. Run your fingers across the dots and you feel the slope, the way the path tilts a little from what pure gravity would sculpt. That tactile sense becomes knowledge. How porous the surface might be, how quickly heat moves through it, whether loose dust mantles the active spots or if the crust is patchy and thin. We can't land a probe on 3i Atlas, but the shift lets us interrogate it from afar. Of course, the door is always open for surprises. If the drift were to reverse in a way that makes no thermal sense, or spike suddenly without a matching outburst in brightness, scientists would look harder. They would ask if a small fragment broke off, reducing mass and changing how easily sunlight and gas can push it. They would consider whether the shape changed, exposing a new vent. They would scour the data for new systematics. Shifting is a measurement, not a conclusion, and good science keeps a little doubt alive so that genuine anomalies can be recognized rather than explained away. In the end, calling it a shift is a compact way of saying, the sky is telling us about gentle, constant forces that don't care whether we're paying attention. With 3i Atlas, we are paying attention. We're stacking images, timing exposures, comparing predictions to reality, and letting those tiny mismatches teach us about ice, dust, spin, and sunlight. Gravity draws the melody. The shift is the harmony. Quiet, easy to miss. But once you hear it, you can't unhear it, and it changes how you understand the whole song. To understand why the path of 3i Atlas is drifting, you have to picture what sunlight does to a fragile, icy body that has spent eons in deep cold. At a distance, it looks like a quiet point. Up close, it's a breathing world. The surface is a patchwork of darker crust and brighter frost. Beneath that, a labyrinth of pores, cracks, and voids holds ancient ices. When daylight crawls across this landscape, the top skin warms just enough for certain ices to change straight from solid to vapour. That vapour snakes through the pores, finds a weak spot and escapes into space. Every breath is a jet and every jet is a push. Tiny, yes, but relentless. Over days and weeks, those whispers of push add up to a measurable nudge, the invisible hand guiding the track of 3i Atlas. Not all ices wake up at the same time. Some need only a gentle touch of warmth. Others demand a closer approach to the sun, so the activity turns on in stages. Far out, the most easily stirred ices start to seep, painting the object with the faintest haze. Closer in, more stubborn ices join the chorus, pressures build under the crust, and sudden puffs or steady jets bloom from vents, cracks and pits. The surface is not smooth, it's a quilt of terrains with different habits. A dark, dusty patch drinks in heat and becomes a hotspot. A bright, reflective patch stays cooler and slumbers longer. This mosaic means the push isn't uniform. It has a preferred direction that depends on which patches are lit and how the object spins. Spin is the metronome of the whole show. If 3i Atlas rotates neatly, the same face turns to dawn, bakes at noon, cools at dusk, and chills through the night. Vents on that face switch on and off with a rhythm you can almost hear. If the rotation is messy, tumbling instead of twirling, the sunlight sweeps across unfamiliar ground each day, and the pattern of jets becomes more complicated. Even then, the chaos averages into a trend. Think of a rotating lawn sprinkler on a slow-moving cart. The spray is all over the place in the moment, but the cart still drifts in one direction over time. That average drift is what observers plot from night to night as the shift. The jets do more than push, they sculpt. Gas carries dust with it, from powdery grains to sand-like bits and sometimes pebbles. The biggest grains fall back, settling into dunes and aprons around vents, mantling the surface with a blanket that insulates the ice below. The finer grains escape, spreading into a pale coma that makes the object look a little fuzzier than a star. This dust coma reflects sunlight and feeds a tail that points mostly away from the sun. The tail itself can fork into personalities, a straighter component shepherded by the solar wind, a broader, curved one ruled by sunlight's steady pressure on grains of different sizes. To the eye, it's delicate. To the physics, it's momentum leaving the nucleus, and the nucleus gently recoils. Beneath the crust, heat doesn't penetrate very far. Only a thin layer feels the day-night cycle. Deeper down, temperatures hardly budge. That shallow skin depth creates timing. The surface warms fastest in the afternoon, and vents often peak a little after local noon, when heat finally sinks far enough to reach the volatile pockets. That lag means the strongest push doesn't line up exactly with the direction to the sun. It skews a bit, like a weather vane catching a gust from off-center. Multiply that skew by millions of rotations and you get a preference in the path shift. Subtle, but real. Seasonality matters too. If 3i Atlas has a tilted spin axis, it experiences seasons as it journeys through sunlight. One hemisphere may bask for weeks, while the other dozes in cold. As the seasons flip, so do the active zones. A dormant patch can wake suddenly, and a vent that had been the star of the show can fade. From Earth, that change appears as an evolving character in the shift. The magnitude of the nudge grows, plateaus, then softens. The direction inches around as new vents dominate. This is why long, patient monitoring is gold. Activity isn't a switch, it's a living schedule. Sometimes the crust fails. Gas pressure builds under a sealed cap of dust and sintered grains, and then, pop. A fragment lifts, a slab slides, or a mini avalanche spills debris downslope. For a few hours or a day, the brightness leaps as fresh, volatile ice stares directly into the sun. The coma swells, jets sharpen, and the push spikes. These outbursts are the fireworks of comet physics, rare enough to be thrilling, common enough that watchers hope for them whenever an active object wanders closer. If 3i Atlas throws even one such flare, the data will show a sudden kink in the residuals and a corresponding change in its light curve, a paired signature of dust and dynamical kick. Every grain that leaves carries a story about where it was born. Large, compact grains suggest a sturdier crust that had to be pried loose. Feathery, fragile grains hint at a fluffy mantle that sunlight can loft with ease. The colour of the coma, slightly red, neutral, or something in between, whispers about organics, minerals, and ice coatings that formed around another star. Gas has its own vocabulary. Certain simple molecules glow when sunlight excites them. Through a spectrograph, even a thin breath can appear as faint lines that come and go as activity rises and falls. Each detection is a clue about the pantry inside 3i Atlas, about which ices are shallow and which are buried, which vents are clean and which pass through long, dusty chimneys. Over time, activity reshapes the body. Repeated outgassing from a single vent can carve a pit with terraced walls. Dust that falls back can armour the surroundings, choking off weaker leaks and funneling action into a few persistent sources. Ridges sharpen, flats gather drifts, and once sharp features soften under endless sprinklings of fallback powder. That evolution feeds back into the dynamics. A narrowed vent collimates its jet, making the push more directional. A collapsed cavity spreads the flow and weakens the thrust. What looks like a simple point of light is actually a changing landscape with weather of its own. All the while, sunlight plays a second role as a gentle, constant wind. Photons bounce off the object and off the dust it sheds, each bounce a tiny tap. On a grain of dust, that tap is substantial. On the larger nucleus, it's feeble but not zero. Add in the warmth the body re-radiates after each day's bake, and you get another steady nudge. None of these forces rivals gravity in strength, but gravity is honest and predictable, and predictability makes faint deviations stand out. Against the steady drumbeat of the sun's pull, even a whisper becomes audible if you listen long enough. The choreography becomes clearest when you tie brightness to motion. As the coma strengthens, the reflected light increases faster than distance alone would allow. At the same time, the measured positions slide away from the purely gravitational path in a smooth, sunward-aware way. Put those two curves side by side and they often rise and fall together. That coupling is the fingerprint of comet physics at work. Light betrays dust and gas betray jets, and jets betray the push that shifts the track of 3i Atlas. There's a practical art to modelling all this without getting lost in details we cannot see. Instead of mapping every vent, astronomers capture the average behaviour. They allow for a small, sun-related push whose strength changes with distance and whose direction can tilt a bit from the purely radial line. Into that simple scaffold they pour real measurements, night after night. If the model keeps predicting tomorrow's position within a small circle, it earns trust. If it starts to miss, it is pared back or adjusted. The sky is the referee. From a storytelling angle, the beauty of these invisible hands is how ordinary they are. No hidden engines, no miraculous forces, just ice waking in sunlight, gas searching for a route to freedom, dust drifting in a breeze, and a spinning, lumpy world responding with a slow shuffle across the starfield. Yet from these humble ingredients, we can tease out deep facts. How porous the interior is, how tough the crust, how quickly heat flows through the top layers, how active or quiet a traveller from another sun can be when it meets ours. And because 3i Atlas is interstellar, every small conclusion travels far. If the push is strong even when it's still far from the sun, that hints at a store of very volatile ices near the surface, perhaps a signature of the nursery where it formed. If the push is weak until it is quite close, that hints at a tighter skin, a world that has been baked before or armoured by fallback dust. If the direction of the push keeps drifting, seasons and obliquity are at play. If it steadies, perhaps a single dominant vent rules the day. Each possibility reduces the space of stories we can tell about how and where this object was made. All this talk of jets and dust can make the phenomenon sound violent. Most of the time it isn't. The majority of the momentum leaves in a soft exhale, not an explosion. The activity is barely enough to lift a handful of sand from the palm of your glove if you were standing there. But in the arithmetic of orbits, barely enough is plenty. The universe keeps generous ledgers for small, steady actions. So when we say the path of 3i Atlas is shifting because of comet physics, we mean that the sun woke up a sleeping miner in its crust, handed it a pickaxe of heat, and let it work, chip by chip, breath by breath, until the entire course traced on a star map moved a little from the ideal. It's the gentlest way a world can announce itself, not by roaring, but by breathing. And if you know how to listen, that breath tells you where it came from, what it is made of, and how it lives in the one brief season when our light falls upon it. Sunlight is not empty. It may feel like pure brightness to our eyes, but to small things in space it behaves like a very gentle wind, each photon a tiny tap on whatever it strikes. Over a single heartbeat, that push is laughably small. Over millions of heartbeats, it is not small at all. Dust, pebbles, even the compact nucleus of 3i Atlas feel this tap, and the way they respond depends on the simple balance between their mass and the area they present to the sun. Put plainly, wide and light things drift more. Compact and heavy things shrug it off, until time makes the shrug meaningful. Start with the dust. When sunlight hits a grain, some of the light bounces, some is absorbed and later re-emitted as heat. The bounce and the glow both push. For a grain the size of smoke or fine sand, that steady push can rival or exceed the sun's gravitational pull on that grain. That is why dust tails bloom away from the sun. The smallest motes are driven fastest into long straight streamers. Slightly larger grains curve along gentler paths. The biggest chunks barely care and hang closer to the nucleus before slowly peeling away. From far away, the tail looks like one smooth brushstroke. Up close, it's a sorting machine powered by light. Now scale up from dust to the body of 3i Atlas itself. Compared to a dust grain, the nucleus is massive, so the same push has a smaller immediate effect. But sunlight never stops arriving, and the nucleus never stops absorbing and re-emitting heat. That steady thermal glow acts like an exhaust, giving the body an almost undetectable thrust. The direction and strength of that thrust depend on how heat moves through the surface. If one side warms and cools quickly, it will radiate more forcefully during the afternoon and early evening of its local day, tilting the net push in a consistent direction. If the surface is slow to warm and slow to cool, like a stone that stays hot after sunset, the timing shifts, and so does the direction of the push. Spin complicates and clarifies this picture at the same time. As 3i Atlas turns, different longitudes face the sun and then face the night. A fast spinner smears the heating around the equator, often producing a push that leans along or against the direction of travel. A body with a pronounced tilt in its spin axis will experience seasons. One hemisphere spends longer basking than the other. That seasonal bias can add a slow, steady component to the push, gently raising or lowering the object's path over months. In both cases, the key is delay. Heat lags behind sunlight. That lag creates the off-center thermal recoil that, night after night, adds the tiniest nudge to the orbit. Surface texture matters in ways that sound fussy but add up. A crust blanketed in fluffy dust is an insulator. It keeps daytime heat close to the skin and releases it quickly after sunset. A crust that is compacted and rocky lets heat sink a little deeper, changing when and where that infrared exhale is strongest. Dark patches soak up sunlight and run hot. Bright patches reflect more and stay cool. Cracks and pits create microenvironments where heat can pool or vent. Put all this together and you get a patchwork of tiny thrusters that you can't see directly, but can infer from how predictions and positions slowly part ways. Light does more than push, it twists. Because the push depends on shape and reflectivity, an irregular body doesn't just get nudged, it can be torqued. Over long spans, that torque can quicken or slow the spin, and even tilt the spin axis. A slight change in spin changes how the surface heats. Change the heating and you change the direction of the thermal exhale. Change that direction and you change the path a little more. It's a feedback loop written in sunbeams, subtle on human timescales, consequential on celestial ones. If observers find that the brightness of 3i Atlas, the telltale heartbeat of its rotation, drifts in period over months, they'll suspect sunlight's twisting hand at work. These effects do not act in isolation. Outgassing jets, described earlier, can dominate when activity is strong, but sunlight's shove is always present, before the first vent wakes and after the last one falls silent. That continuity makes it a quiet baseline. When the coma thins and gas fades, the small non-gravitational drift that remains is a signpost pointing back to light and heat. Modelers use that signpost to keep predictions tight. Ignore it, and a telescope scheduled to recapture 3i Atlas next month might aim at empty sky. Include it, and the object appears exactly where the model says, a triumph built from tiny forces patiently accounted for. Distance from the sun sets the tempo. Far out, sunlight weakens and both radiation pressure and thermal recoil soften. Nearer in, they strengthen, but composition can override that simple rule. A darker surface absorbs more, so a dark traveller can feel a stronger thermal push than a brighter one at the same distance. A surface that conducts heat well will smooth out day-night extremes. One that does not will make afternoons punchier and nights colder, changing when the strongest thrust occurs. Even the size of 3i Atlas plays a role. Smaller bodies generally respond more to sunlight's push, because their area, the part that catches photons, is large compared to their mass. From Earth, we see these invisible hands through timing, geometry, and patience. If the non-gravitational drift grows and shrinks in step with solar distance, but lingers even when gas activity is low, sunlight is the prime suspect. If the direction of the drift matches what you'd expect from a warm afternoon hemisphere, or from a long summer in one hemisphere, that's another clue. If the rotation period edges shorter or longer over many weeks, the twisting action of light may be changing the spin itself. None of this requires a single breathtaking image. It requires many modest images, carefully calibrated, and a willingness to let the smallest mismatches teach you what force is at play. Dust dynamics offer a second window into the same physics. Watch the tail close to the nucleus, and you'll see multiple strands. One composed of the freshest, finest grains blown nearly straight away from the sun, another made of heavier grains that curve gently because motion and light push compete more evenly. By modelling those strands, astronomers back out how strongly light is pushing on different sizes of dust, and in turn what mixture of sizes the vents are releasing. That mixture reflects the surface grip. Tight crusts yield coarser grains. soft mantles release fluff. Even here, sunlight is both painter and analyst. Painter because it draws the tail. Analyst because its push allows us to decode what we're seeing. Because 3i Atlas is not from here, the sunlight story becomes a biography clue, not just a physics lesson. If its surface responds with an unusually strong thermal recoil far from the sun, perhaps its crust is darker or more porous than typical solar system comets, a hint about the star and disk where it formed. If the response is subdued until high illumination, perhaps past passages near other stars heated and hardened its skin, leaving a rind that only intense sunlight can influence. Its tilt, the steadiness of its spin, and how quickly those change under solar prodding can all whisper about how long it has wandered, and how often it has been baked by other suns. It's tempting to imagine sunlight as gentle and forgettable, something that merely lets us see. For small worlds, it is also an artist and a sculptor, a navigator and a watchmaker. It draws the tales we marvel at, sets the rhythm of day and season, winds and unwinds the spin with patient fingers, and nudges the path of 3i Atlas just enough that careful eyes can tell. Gravity writes the main plot. Sunlight edits the margins. Those edits accumulate into meaning, into a slightly different arrival time at a checkpoint in space, into a tail with a slightly different curve, into a rotation that is a touch faster by the next apparition. So when astronomers say sunlight has weight, sort of, they are offering a translation for the camera. Photons carry momentum, and momentum exchanged is motion changed. No equations are needed to feel it. Hold a sunlit flag and you'll see it strain in a breeze. Imagine a version of that breeze made of light itself, touching a body that gives nothing back but the faintest constant exhale of heat. That is the quiet force at work on 3i Atlas every second of its visit. It is patient, it is predictable, and in the patient, predictable residue of many nights' measurements, it becomes visible. The signature of light, written on a traveller from another star. The first two interstellar visitors arrived like mismatched siblings, each teaching a different lesson about what alien small bodies can be. The earlier one, the one everyone remembers for bending the rules, slid through our backyard without a visible coma, yet it still wandered off the gravity-only path by a hair. That told us two things at once. First, gentle non-gravitational forces can matter even when you don't see dramatic tails. Second, the look of a visitor can mislead. A dry face does not guarantee a quiet interior. The second traveller, by contrast, behaved like a textbook comet. Fuzzy from the moment we got a good look at it, with gas and dust streaming away, colours and spectra that match the familiar class, and even a tendency to fragment as it rounded the sun. That pairing, enigmatic drifter and classic comet, stretched our expectations in opposite directions. Now comes the third data point, and the question becomes which playbook will apply when we watch 3i Atlas up close. Start with the hard-won humility from the first visitor. Our telescopes caught a faint, elongated body, whose brightness flickered in a way that implied an odd shape and an unsettled spin. No obvious gas lines shouted comet, and yet the trajectory showed a tiny, steady shove that you'd usually blame on outgassing or on the way heat re-radiates from a warm surface. The lesson was not that something supernatural was happening. The lesson was that small forces can masquerade as mysteries when data are sparse, and that an object can be active in ways that are barely visible. For 3i Atlas, that means we should be ready to detect activity by its consequences, changes in path, subtle halos, before we can see it outright. If the brightness stays star-sharp but the orbit keeps asking for a non-gravitational nudge, we've seen that movie before, and we know how to watch it patiently. From the second visitor, we learned the opposite kind of caution. Sometimes things are exactly what they look like. It arrived trailing the familiar signatures, gas emissions that waxed and waned with sunlight, a dust tail that sorted grains by size, and a nucleus that shed material when stresses peaked. Its spectra looked reassuringly normal for a comet, and if you plotted its motion nightly, the deviations from gravity matched what you'd expect from vents that wake near local noon and take a nap after dusk. That grounded our models. It told us that the recipes we use for homegrown comets still work for a world forged under another star's light. For 3i Atlas, that means we should try the simple model first. Assume sunlight warms a heterogeneous crust. Assume some vents dominate. Assume the push they produce leans slightly away from the sun, and changes with distance. If the fit holds night after night, the simplest explanation earns the lead role. Both visitors taught us about spin in different ways. The first seemed to tumble, a reminder that not every small body spins like a neat top. Tumbling changes how sunlight paints the surface, and it can turn even modest outgassing into a push that wobbles around before averaging out. The second gave us a clearer, calmer light curve and a more stable sense of day and night on the surface, letting us tie changes in brightness to specific geometric moments. For 3i Atlas, the moral is to measure rotation early and keep measuring. If the light curve is chaotic or drifts in period, that hints at sunlight's subtle torque or at ongoing reshaping by outgassing. If it's steady, we can map activity onto a clock and predict when the strongest nudges will arrive each day. Composition was another fork in the road. The first traveller's lack of obvious gas lines forced a decade of creative hypotheses. Extremely volatile ices that leave little trace, a crust that's sealed in vapour, or dust so fine that any coma blended into the starlight. The second visitor's chemistry was cheerfully loud. Carbon-bearing gases, water-related signals, a suite of lines that matched our comet libraries with minor quirks and a few delightful surprises. That contrast taught us not to overfit personality from one example. With 3i Atlas, even a few good spectra will go a long way. A faint, broad colour slope can suggest space-weathered organics. A shy emission line can betray a vent that only wakes for a few hours each rotation. A stubbornly featureless spectrum can warn us that most of the action is dust, not gas. The point is not to jam it into one past mould or the other, but to let its voice be heard long enough to know which chorus it belongs to. Size and strength matter too. The first object's smallness amplified every subtle force. A tiny push from sunlight or gas translated into a noticeable drift over time. The second, being larger and actively shedding material, broadcast its physics in a different register. Brighter, easier to track, but also more chaotic near perihelion, with fragmentation events that briefly rewrote predictions. 3i Atlas could land anywhere along that spectrum. If it is small and inert-looking, we should expect the story to be written in tiny, consistent mismatches between model and measurement. If it's bigger and dusty, the story will splash across images as tails, fans, and occasional outbursts that spike the light curve and kick the path. Either way, we've learned how to read both kinds of handwriting. There were sociological lessons too. The first discovery showed how quickly speculation can sprint ahead of data when the object is faint and the window is short. The best antidote was more measurement from more eyes and relentless cross-checks between teams. The second showed the power of broad coordination, amateurs and professionals, short exposures and deep stacks, infrared searches for warm dust and radio hunts for larger grains. 3i Atlas benefits from both experiences. Surveys are faster now, pipelines cleaner, and the global relay more practiced. We know to bank pre-coveries by stacking older images at the predicted rate of motion. We know to chase sunrise and sunset windows where thermal contrast can be most revealing. We know to keep quiet in public claims until multiple reductions agree. Even tail geometry became a teacher. The first visitor had no obvious tail, challenging the reflex to equate interstellar with spectacular. The second offered layered tails that told a story about grain sizes and release speeds like tree rings unspooling behind the nucleus. With 3i Atlas, the presence or absence of a tail isn't a verdict, it's a clue. A delicate straight streamer near the sun points to fine dust blown hard by light. A broader curved fan close to the nucleus points to heavier grains escaping more slowly. No tail at all points us back to thermal recoil and subtle jets that hide in plain sight. Timing finally is everything. The first traveller slipped away before many of our best instruments could pivot to it. The second stayed bright and cooperative long enough for a symphony of observations. Because of those experiences, the observing playbook for 3i Atlas writes itself. Get astrometry early and often, lock down the rotation period if possible, secure low-resolution spectra soon to catch volatile lines before geometry and distance bury them, schedule deep imaging at multiple phase angles to tease out dust and coma structure, and revisit all of it as the Sun-object-Earth geometry evolves. Each of those steps exists because we learned, sometimes painfully, what happens when you miss one. Put all the lessons together and a simple truth emerges. One interstellar object can be a riddle, 2 can be a false dichotomy, 3 begins to look like a pattern. Maybe the pattern will be that interstellar visitors split into quiet, recoil-driven drifters and noisy comet-like shedders. Maybe it will be a continuum shaped by size, spin and crust. Maybe we'll find seasonal behaviour to be common, or tumbling to be rare, or vice versa. Whatever the outcome, 3i Atlas does not have to be shocking to be important. It just has to be itself long enough for careful eyes to watch. And thanks to the mismatched lessons from those first two guests, we're better prepared to see it clearly, whether it arrives whispering like a stone that breathes, or singing like a comet that finally found sunlight again. The first orbit you draw for a new object is a sketch done in pencil, not ink. With only a handful of positions, the sky allows many stories that all look plausible. Each story is an orbit, some bound, some unbound, some grazing the planets, some not, and they fan out into a cloud of possibilities. As hours turn to nights, you lay down more dots on the starfield, and that cloud begins to collapse. For 3i Atlas, those early nights were all about herding possibilities into a single coherent path. The process isn't dramatic to watch, but it is one of the great quiet arts in astronomy. You rewrite the orbit by listening to where the sky says the object actually is, not where your first guess hoped it would be. Imagine 1,000 near-identical futures for 3i Atlas, each future represented by a ghostly point that marches across tomorrow's sky. Those are clones, trial orbits that all fit the current data within the uncertainties. Point a telescope where the densest part of that ghost cloud sits, and you're likely to catch the real thing again. Miss a night, and the cloud spreads. Catch a night, and it tightens. This is the rhythm of orbit refinement. Predict, observe, update, repeat. The update step is where the pencil sketch gains ink. You weigh each new measurement by its quality, you test whether it plays nicely with the rest, and only then do you let it tug the solution in its direction. Quality begins with calibration. Positions are measured against star catalogues that fix the celestial grid with exquisite accuracy. The best reductions correct for how the atmosphere smears starlight, for how a camera's optics slightly distort the field, and for the tiny colour differences that can shift a centroid by a fraction of a pixel. A good reduction makes a faint point behave like a ruler's tick mark. A great one turns that ruler into a yardstick. With interstellar travellers like 3i Atlas, that yardstick matters, because the object is faint, fast, and available only for a short window before distance and glare steal it away. Once measurements leave the observatory and reach the orbit solvers, the numbers must survive an inquisition. Do they line up with last night's preferred path? Do they bend the line only a little, in a direction that makes physical sense? Or do they demand an acrobatic twist that hints at a bad timestamp, a hot pixel, or a plane streak hiding in the noise? Outliers happen, and they are mercilessly tested. Keep the good, quarantine the suspicious, and, when several teams independently see the same subtle bend, let the orbit absorb it. That's how rumours become results. With 3i Atlas, the first sketch said, unbound. Its path opened outward, the calling card of something not tied to the sun. Then came the refinement. Planets add their small tugs, and you include them. Light and heat add their tiny pushes, and you consider them if the residuals, those nightly differences between prediction and reality, lean consistently in one direction. You don't throw in every possible effect at once. You start with gravity, because gravity is the big engine of the tail. When gravity alone keeps missing by the same small amount, you allow a gentle sun-related nudge. If the misses shrink and keep shrinking as more data arrive, you keep the nudge. If they don't, you back it out. The orbit isn't a monument, it's a living document. This living document is summarised for observers as an ephemeris, a timetable that says, at this hour, in this patch of sky, look here. Early on, those patches can be big, search boxes rather than pinpoints. As the orbit hardens, the boxes shrink. There is a quiet thrill in watching that shrinkage. It means you have earned the right to use smaller telescopes, shorter exposures, and tighter schedules. Teams begin to plan more daring things. Spectra when the object is still dim, deep images to catch faint halos of dust, perhaps even radio or radar attempts if geometry and brightness allow. Each of those plans depends on the ephemeris being right. Rewriting the orbit isn't academic. It keeps telescopes from staring at empty sky. Certain observing moments have outsized power to reshape the solution. When 3i Atlas is low in the sky, the air adds jitter to positions. When it's high and the stars are sharp, each dot carries more weight. When its motion on the sky is almost straight toward or away from us, a small timing error can masquerade as a bigger position error. When the motion is sideways, the geometry makes the measurement more robust. The best teams exploit this by spacing observations to capture different angles and rates, feeding the solver varied information instead of a stack of near-identical points. Variety cuts uncertainty. Repetition alone just deepens the rut. Sometimes the best way to rewrite tomorrow's orbit is to rewrite yesterday's. Precovery searches comb through old survey images, stacking along the expected rate and direction to tease 3i Atlas out of the background on nights before discovery. 1 week honest detection a week earlier can be worth a dozen average ones tonight. It lengthens the arc, and a longer arc is the currency of certainty. With that longer arc, the cloud of clones collapses much faster, and predictions stop wandering. Then there is the moment when the data begin whispering about a force you didn't include. If, night after night, the residuals are a little sunward, or a little along the path, it's a clue that sunlight and heat, or gentle outgassing, are adding their own punctuation to the trajectory. You don't leap to complicated maps of vents and seasons. You add a simple term that stands in for a small push that grows nearer the sun. If the fit improves and stays improved as conditions change, you've learned something real. That small push is not just bookkeeping, it is personality. It tells you that 3i Atlas is breathing, even if the coma is too thin to see directly. Perihelion, the moment of closest approach to the sun, is often where orbits either sing or squeak. Geometry changes quickly, brightness climbs, activity can spike, and the skyplane path bends in ways that give solvers leverage. It is also where mistakes grow teeth. An unmodelled nudge can throw predictions off by enough to lose the target in glare or twilight. That's why perihelion campaigns look like air traffic control, handoffs across longitudes, backups planed for bad weather, and fast reductions that feed fresh positions back into the global loop within hours. The reward is a post-perihelion orbit that is tighter and more honest than anything possible before the swing around the sun. Planetary encounters add their own flavour. 3i Atlas won't be captured, but a distant brush with a giant planet can ever so slightly deflect its path. Good solvers include those tugs automatically. Great solvers keep an eye on whether tiny mismatches around those dates hint at something more. Maybe a dust outburst that offset the gravity-only bend, maybe a temporary brightening that shifted measured centres by a hair. When the orbit and the photometry are read together, the story becomes richer than either on its own. Light curves, the gentle up-down heartbeat of brightness, as 3i Atlas rotates, matter in this chapter too. A complex or changing light curve can signal a tumble, and a tumble can make non-gravitational pushes wobble before they average out. If the rotation period drifts over weeks, sunlight's torque might be tweaking the spin, which in turn tweaks when and how strongly certain patches of the surface warm and vent. Orbit solvers don't directly ingest the light curve, but humans do. They carry it in their heads when deciding whether a small time-linked deviation in position is believable physics or a reduction artifact. The more context you have, the safer your edits to the orbit become. Between updates, the orbit breathes through uncertainty cones that are shared with observers. These aren't just circles on a finding chart. They represent the range of futures still compatible with the past. Schedulers aim telescopes not just at the centre, but also through the edges when the weather or moon will soon erase a window. If a night's attempt hits the edge and the object is found there, the whole cone slides and shrinks in a gratifying snap, the way a puzzle piece locks when you've been trying close fits for minutes. If the field is empty, that absence is also data. It tells you which futures just died. Every so often, a single astonishing measurement rewrites everything at once. Radar would do that. One clean range and speed can collapse skyplane uncertainties to almost nothing. But interstellar visitors are usually too faint and too far for radar to grab. More often, the showstopper is a deep precovery or a run of astrometry, with brilliant seeing that slices residuals in half. After such nights, the orbit files updated for 3i Atlas feel different to the teams who read them. Predictions become confident not for hours but for weeks. The language in emails changes from likely to certain, enough to risk precious time on the big telescope. All of this care depends on not falling in love with the last solution. The discipline is to treat each orbit as the best story so far, not the final word. You label versions, you keep the history, and you compare new fits to old ones to check that improvements are real and not just the product of an overeager model. You resist the urge to add unnecessary complexity. You also resist the temptation to stay too simple when the sky is begging you to admit a new force. The right orbit is the one that makes the smallest number of honest assumptions and still nails where 3i Atlas will be tomorrow at dawn. There is a human tempo to all of this. The hum of observatories at night, the clatter of keyboards at breakfast as reductions land, the mid-morning push that turns a stream of positions into a new ephemeris that goes right back out to the world. The loop repeats, and with each loop the object becomes less of a rumour and more of a map traveller. Rewriting the orbit is not about erasing the past, it's about ink over pencil, clarity over guesswork, and a steady approach to truth that only patience and cooperation can buy. By the time the campaign is mature, the orbit of 3i Atlas reads like a polished paragraph rather than a draft. You can tell, at a glance, how sensitive the path is to sunlight's touch, how much the planets matter, and how quickly small errors would grow if you stopped observing. You can state with a straight face where it will pass in relation to a star field 2 weeks from Thursday and be right within a small, well-earned circle. That circle is the signature of the work. Thousands of photons caught and calibrated, hundreds of dots turned into a curve, and a curve refined until prediction and reality finally shake hands. It's just as important to clear the fog as it is to chase the signal. When people hear that the path of 3i Atlas is shifting, imaginations sprint to collisions, secret engines, cosmic portents. Start by ruling out the loudest mirages. A measured drift in position does not mean guidance, menace, or miracle. It means physics so small that only careful, repeated observations can hear it. Sunlight pushing, heat exhaling, pockets of volatile ice breathing through cracks. Those are the usual suspects, and they make honest, boring sense. Not on a collision course is the first, most useful statement. The object's track opens outward, a classic signature of a passerby that fell toward the sun and will depart again. As new measurements arrive, astronomers fold them into the orbit, and the prediction boxes shrink rather than jump into alarm. If a genuine impact scenario existed, it would not be a rumour. It would appear in the ephemerids everyone uses, the sort of sober numbers that drive telescope schedules. The fact that teams continue to observe 3i Atlas with long, patient cadences instead of emergency campaigns is itself a quiet verdict. Interesting, not dangerous. Not under intelligent control comes next. The non-gravitational nudge that improves the orbit fit is small, sun-aware, and consistent with outgassing and thermal recoil. It waxes as the object receives more light and wanes as it recedes. If you watch the brightness flicker with rotation and compare that rhythm to how the tiny drift evolves, they line up the way natural vents and warming patterns would. There is no sudden lateral acceleration, no sharp, deliberate course changes, no radio beacons, no signatures of power beyond sunlight. The path is gravity's melody with a soft harmony from heat and gas, no hidden hand turning a wheel, not a rogue planet, not a mini-moon. The brightness, once corrected for distance and viewing angle, implies something much smaller than a world that could bully or trap nearby bodies. Its presence does not tug planets in ways we could measure, nor does it carry the inertia to rework the solar system's tides or fields. This is a small traveller by planetary standards, a speck with personality, not a heavyweight with agenda. Not about to flip around or pull stunts that violate momentum. The forces at play are gentle and continuous. Outgassing jets act like a pocket full of tiny thrusters that pulse with daylight. Thermal recoil is a steady exhale. They can bend the path a little, they cannot make a U-turn. The energy bookkeeping is relentless. You cannot get a dramatic reversal from the kind of slow, sun-driven processes we're seeing, not a harbinger of earthquakes, storms, or solar tantrums. Nature tempts us with coincidences. A bright visitor appears, something else dramatic happens. A story writes itself. But small bodies like 3i Atlas have no credible mechanism to trigger geologic events across the void. The sun's behaviour is its own, governed by magnetic fields braided deep within it. The Earth's crust answers to stresses stored over years, not to a faint pinprick drifting through the inner system. Correlation is not causation, and the physics here refuses to be drafted into folklore. Not Planet X in disguise, not the perennial hidden giant. If an undiscovered massive world were roaming nearby, it would reveal itself through the motions of many objects, not by one comet-scale visitor drawing headlines. Surveys that found 3i Atlas are exquisitely sensitive to slow, bright movers. The sky is combed more completely than at any time in human history. What slips through are faint, fast, small things, exactly like this. Not a radiation hazard. Tails look vast because sunlight paints dust and gas into elegant geometry, not because they carry dangerous energy. The coma is the thinnest of fog spread across huge volumes. Even a spectacular tail contains very little mass. From the perspective of a planet, it's closer to theatrics than threat. If 3i Atlas were to graze Earth's orbit, which its current path does not suggest, you might get a minor meteor shower years later as old dust streams are intersected, not an atmospheric drama. Not a paradox that breaks our models. The shift is exactly the sort of tiny deviation the models predict, once you admit sunlight and sublimation to the conversation. We've seen it on comets, born in our own deep freeze. We've modelled it on asteroids that drift slowly between resonances over many years. What makes 3i Atlas special isn't that these forces exist, it's that they're acting on a visitor from another star's nursery, letting us compare familiar physics to unfamiliar origins, not proof of a grand conspiracy of bad measurements. Independent observatories, different cameras, different nights, different analysts arrive at the same small corrections. The reductions are anchored to precise star catalogues, the timestamps audited, the optical distortions mapped and removed. Outliers are quarantined, precoveries in older images are sought and verified, suspicious frames are thrown out without regret. What remains after that discipline is a story told by multiple instruments in the same quiet voice. Not an object that will suddenly become bright enough to dominate the sky. Popular imagination likes the switch flip, dark pebble to sky-filling omen overnight. In reality, the light curve rises and falls with distance and with moderate bursts of activity. Even a lively outburst tends to be a brief flare that fades as fresh ice crusts over. The spectacle we receive is regulated by geometry and material, not by narrative convenience, not a stealth fragment factory raining hazards. Fragmentation can happen when internal pressures or thermal stresses exceed what the crust can bear, but most breaks produce a family of smaller pieces that continue along nearly the same path. The atmosphere of Earth is ruthless to small fragments, grinding them to dust if they ever wandered into harm's way. The present orbit keeps 3i Atlas a traveller to watch, not a quarry to fear, not a messenger designed for us. It's tempting to see meaning in timing. Our telescopes get good, and the universe sends a postcard. The truer reading is humbler. The sky's full of travellers. Our tools have finally become sharp enough to notice the quiet ones and coordinate quickly when something interesting appears. 3i Atlas is eloquent because we are listening well, not because it chose us. Not a reason to throw out the idea that natural explanations can be subtle. The first instinct when the data are thin is to reach for exotic ideas. The second, wiser instinct after a few weeks of careful tracking is to revisit the boring hypotheses and see if they fit with new care. Time and again they do. Outgassing looks like outgassing. Thermal recoil looks like thermal recoil. Sunlight acts like a patient sculptor. The extraordinary part is not the mechanism but the provenance. This behaviour is written into a rock and ice body that spent its formative years under a different sun. Not a secret that only insiders can check. The ephemerids are public. The coordinates are shared. Amateurs with well-calibrated rigs routinely recapture targets like this and contribute real measurements. That broad visibility is an antidote to anxiety. You can point a telescope where the numbers say and see the same faint traveller that the big facilities see. When reality is open book, mystery has to work harder to survive. Not a shortcut to grand conclusions about life, destiny or doom. Interstellar small bodies do carry chemistry worth debating, dusty organics, ices that record distant conditions, but one object cannot settle questions that span biology and time. What it can do, powerfully, is thicken the plot with data. Tell us whether surfaces out there tend to be crusted or fresh, dark or bright, fragile or tough. Tell us whether spins are usually neat or messy. Tell us whether sunlight and ice dance the same way under other stars. Finally, not a reason to be less curious. Clearing away the false and the frightening doesn't make 3i Atlas dull, it makes it legible. Once you stop worrying about what it isn't, a doomsday stone, a steered craft, a cosmic omen, you're free to notice what it is. A faint, fast messenger whose tiny deviations from the ideal curve are packed with information. The ordinary explanations are more than enough, and they are beautiful in their own right. Light is the first language we share with distant things, and for 3i Atlas it is a language dense with hints. A single, faint smudge on a detector can be stretched into a spectrum, a rainbow where certain colours swell and others thin, and that pattern acts like a fingerprint for material. Even before you split the light, simple colour measurements across a few filters already sketch personality. If the object looks slightly redder than the sun, you suspect space-weathered organics dusting the surface in the coma. If it trends neutral, or even a touch bluer as activity rises, that can mean fresh ice grains are being lofted, reflecting sunlight in a cleaner, brighter way. Track those colours night after night and you watch the surface and near-surface chemistry breathe with the heat of the sun. Spectroscopy deepens the story. When sunlight bounces off dust, it paints a smooth, sloping continuum. When gas escapes, it glows at very specific colours. A classic early sign is a faint violet whisper from simple carbon-bearing molecules, followed by a green glow from oxygen that's liberated when sunlight breaks apart water vapour. Later, as the object awakens more, you look for broader, quieter features from dust. The way grains scatter and absorb light reveals their sizes and coatings. Even a non-detection is powerful. If you do not see certain gas lines when 3i Atlas should be warm enough to let them out, that tells you they're scarce near the surface or that dust is masking the signal. Those gas lines don't just say ice here, they say which ices. Water vapour means shallow, sun-warmed reservoirs. Carbon monoxide and carbon dioxide, if present, can switch on farther from the sun. Catching them hints at deeper, colder pockets, or at layers preserved since the object formed around another star. Each species turns on and off at its own comfort level. Watching the sequence lets you guess the order of layers just below the crust, what's near the top, what's buried, and how the heat flows down. Dust is its own archive. Fine. Fluffy grains scatter blue light differently than compact older grains. Larger particles redden the light they reflect and cling closer to the nucleus before peeling into the tail. By fitting how bright the coma is at different distances from the centre, observers estimate how much dust is being released and how quickly. If the dust production rises while gas lines lag, 3i Atlas might have a crust that breaks easily into powder but keeps its volatiles sealed. If gas jumps first, you get the opposite picture. Vapour forcing its way out with not much grit, at least at the start. Polarimetry, measuring how light's vibration is oriented after it bounces off dust, adds a subtle but powerful angle. Different grain shapes and porosities twist the polarization in telltale ways. A coma full of fragile, porous clumps leaves a different signature than one dominated by compact, glassy grains. When the phase angle changes, the angle between the Sun, 3i Atlas, and Earth, the polarization changes too, and the curve you trace against that angle points to how fluffy or armoured the dust really is. That in turn reflects the violence or gentleness of the vents. A collimated jet tends to fling bigger chunks. A gentle seep lifts little flecks that sunlight can shepherd far. The same phase geometry shapes the colours. Many dusty surfaces redden as the phase angle increases, a phenomenon called phase reddening. If 3i Atlas shows a strong version of that effect, it likely wears a mantle of processed material, organics baked by countless years of cosmic rays and micro-impacts during its long interstellar voyage. If the trend is weak or even goes the other way during bursts of activity, fresh particles may be dominating the light, momentarily erasing the patina. Thermal infrared light, heat, not sunlight, lets you weigh the body from its glow. Combine the reflected sunlight at visible wavelengths with the gentle warmth. 3i Atlas emits in the mid-infrared, and you can separate size from reflectivity. A small, shiny object can look as bright as a larger, darker one in visible light. Their heat gives them away. With that size estimate in hand, every other clue tightens. The same gas brightness translates to a different outgassing rate if the nucleus is bigger rather than smaller. The same dust coma brightness points to different mass loss, depending on the true size. Knowing the reflectivity, the albedo, also speaks to surface texture. Dark, carbon-rich crusts soak up sunlight. Brighter, icy patches speak to recent exposure. Timing is a microscope. Spread your spectra across a full rotation and you watch active patches rotate into daylight. A gas line strengthens for a few hours, then fades, then returns on the next spin. Now you've found a vent and can map it onto a clock. Do that over weeks and you watch seasons unfold if the spin axis is tilted. One hemisphere takes its long summer, the other waits for its turn. If the timing of those spectral pulses lines up with tiny nightly changes in the measured path, you can say not just that activity exists, but that it is the cause of the shift we see in the orbit. Sometimes the most revealing thing you can measure is silence. Set an instrument to a line where a common gas should sing, integrate for a long, careful stretch, and hear nothing. That null result becomes an upper limit you can compare to what the dust is doing. Too little gas for the dust you see. Maybe the grains are being recycled, lifted and falling back. Or maybe the crust is rich in organics that crumble easily without much vapour. Very early in the approach to the Sun, upper limits on the more volatile gases tell you whether 3I Atlas stores super cold ices near the surface or locks them deep. The tail itself is a spectrograph you can see. Near the nucleus you might find a narrow, straight streamer, a ribbon of the smallest grains accelerated quickly by light. Farther out, a broader curved fan betrays heavier grains taking longer to respond. Stack images along those curves and you can back out when each streamer was launched. Those launch times, compared against rotation and solar distance, become a diary of bursts and lulls in activity. Colour maps across the coma add texture. If the inner coma is neutral while the outer coma reddens, small icy grains may be sublimating and leaving behind darker husks as they drift outward. If the inner coma is already red, the nucleus may be cloaked in an aged crust, with only brief cracks exposing anything fresh. During outbursts, watch for a momentary bluing of the light as clean ice crystals flood the inner region, followed by a slow reddening as they sublimate and dust takes over again. High-resolution spectra, when the object is bright enough, peel apart lines into shapes that carry physics. A narrow core suggests calm, slow gas near the vent. Broad wings hint at faster jets or molecules colliding and exchanging momentum. If different gases show different widths or slight shifts in their centres, they may be escaping from different places or being accelerated differently by sunlight. Stack enough of these tiny effects and you start to picture the architecture of the vents even though you cannot see the surface. There's also the trick of subtracting the sun. Astronomers observe a sun-like star the same night and same air mass, then use it to remove the solar fingerprint from 3I Atlas's reflected light. What remains is the object's own character, the way its dust colours and dims that starlight. That solar-removed spectrum can reveal gentle slopes and shallow dips that would otherwise hide. Some dips are associated with iron-bearing minerals, others hint at hydrated phases, though those are subtler and rarer in comets. Any such feature, confirmed carefully, would be a treasure for an interstellar visitor, pointing to processes in a nursery we will never enter. Comparisons are the compass. Lay 3I Atlas's colours, slopes, and gas ratios next to catalogues of solar system comets. If it lands squarely among familiar families, the chemistry of planet-forming disks may be more universal than we feared. If it sits off on its own, dust colours outside the usual spread, weak water with strong carbon monoxide, or the reverse, then we have evidence that other stars cook their small bodies differently. Neither outcome is disappointing. Landing in the crowd means our recipes travel well. Standing apart means nature writes many menus. All of this rests on coordination, because each clue grows stronger when paired with another. A polarimetric spike means one thing by itself. Coupled to a sudden blue-leaning colour change, it screams fresh fluffy grains just released. A faint oxygen glow could be contamination from air glow in Earth's own atmosphere. See it rise and fall in concert with water proxies and it becomes real. A slow drift in rotation period might be an analysis artifact. Watch the thermal glow change in lockstep as the afternoon hemisphere warms and cools, and you trust the spin change and the sunlight torque behind it. 3I Atlas speaks through scarcity as much as abundance. It will never be as bright as a great comet. Its signals will often be whispers inside the noise. That's why observers stack exposures, co-add nights, and share reductions, so that independent pipelines can argue and agree. The goal isn't a single stunning spectrum, it's a consistent story told by many modest ones. When the pieces line up, colours, gas lines, dust behaviour, polarisation, thermal glow, you don't just list ingredients, you infer the kitchen, a crust that is dark and porous or bright and compact, vents that are few and focused or many and leaky, a subsurface layered like pastry or mixed like bread. And because 3i Atlas is interstellar, every small inference stretches far. A dust colour that leans redder than most solar system comets hints at more complex organics in its birth disk. An early appearance of very volatile gases suggests the nursery was colder, or the crust less processed before it ever met our sun. A stubborn lack of certain species could mean they were rare in its home system, or that long, lonely eons in interstellar space have baked them away. Light cannot answer every chemical question. Some ratios and isotopes are beyond reach without a probe, but light can narrow the field from infinite stories to a handful worth believing. And that is the quiet power of watching a rainbow from a visitor that will never circle back. It lets us read, line by line, what another sun wrote into a small body long ago. Spin is the hidden engine behind everything we're seeing. How fast 3i Atlas turns, how its axis is tilted, and whether it spins cleanly or tumbles chaotically, all of that decides which patches of the surface get baked, which vents wake up, and when those tiny jets push hardest. The shape sets the stage. A stretched, lumpy or bilobed body reflects and re-radiates sunlight unevenly. And that unevenness becomes motion you can actually measure across nights. Get the spin and shape wrong and the rest of the story. Activity, brightness changes, even the shift in its path won't line up. The first way we meet that spin is through a light curve. A slow pulse as 3i Atlas brightens and dims over hours. If it were a perfect sphere with a uniform surface, the light would be steady. It never is. A tall amplitude, big swings between bright and faint, suggests an elongated or highly irregular shape turning like a baton. A smaller amplitude can mean a rounder body, or it can mean an elongated body seen end on, so the cross-section doesn't change much. That's why observers chase this pulse across many viewing angles. When Earth and the Sun shift relative to the object, the amplitude should change. If it doesn't, the surface might be patchy in albedo, light and dark areas, rather than dramatically misshapen. If it does, shape is taking the lead. To sort those possibilities, teams watch the colour as it pulses. If the brightness changes while the colour stays steady, geometry, shape, is probably driving the show. If the colour swings along with the flux, then darker and brighter terrains are rotating in and out of view. One rotation is rarely the whole story. Small bodies love to spin in complicated ways. A clean single-period light curve, up, down, repeat, says 3i Atlas could be in principal axis rotation, the neat top-like state. But throw that light curve on the wall for a few nights, and sometimes you'll see beats and side rhythms, a hint of non-principal axis rotation. Tumbling. Tumbling means the object is rotating around more than one axis at once. That matters, because sunlight, and any outgassing vents, then sweep across the surface in shifting patterns. A vent that was in darkness last cycle might catch a few hours of glare this cycle. The resulting jets don't just push, they torque, and those torques can either damp the tumble slowly or pump it up, depending on where the vents sit. Detecting a tumble comes from those telltale multi-peaked light curves, from period drifts, and from the way the pulse shape itself morphs as viewing geometry changes. What sets the spin in the first place? 3 sources: the fossil memory of whatever flung 3i Atlas out of its home system, sunlight's patient twisting over eons, and once it gets close enough to our sun, its own jets. Sunlight can slowly torque an irregular body, the way uneven heating and re-radiation give a tiny, steady twist. That's a background hum, always there. Jets are the drum fills. A vent near a ridge that fires every local afternoon puts a push not just on the path but on the spin rate. Over weeks you can get measurable changes, a spin up if the torque aligns with the rotation, a spin down if not. Sometimes the changes come in steps after outbursts, as a chunk collapses or a vent widens. Watch the rotation period carefully, and you can see those steps arrive like the tick of a second hand you didn't know the clock had. The axis tilt, the obliquity, is the season maker. A pole tipped over means one hemisphere soaks in a long summer, while the other shivers through night. Then they trade places as the orbit carries 3I Atlas along. In practice, that shows up as activity zones that migrate. Early on, vents at mid-latitudes might dominate. Later, the polar regions wake. The light curve follows. The phase of the pulse shifts a little each week, and the amplitude can grow or shrink as bright jets contribute extra light when the active terrain faces us. The path shift follows too, because the direction of the strongest thermal exhale and the thrust from jets both track with where the sun hits hardest. Solve the pole, and you've solved half the riddle of how and why the orbit is drifting. Shape inversion, turning a stack of light curves taken at different angles into a 3D outline, is the art that stitches this together. You don't get fine details, you get a convex hull that captures the overall elongation and the major lobes. For a traveller with a coma, this is harder. The nucleus hides in a faint halo. Teams fight back by tracking non-sidereally, so the nucleus is sharp and the starfield smears. They subtract a point spread template to peel away the coma. They use short exposures to catch the nucleus before the halo swallows contrast. Do this well, and the reconstructed shape starts to make sense of the pulse. That bump in brightness every half rotation is the big lobe turning broadside. The shallower valley is when we're peering end-on. If 3I Atlas is actually a contact binary, two lobes resting together, the model will prefer a peanut silhouette, and the light curve will often favour a double-peaked rhythm. Inside, structure decides how spin changes are absorbed. A monolithic shard can transmit torque rigidly. A rubble pile, a gentle congregation of boulders and dust held together by meagre gravity, and a bit of cohesion can flex and rearrange. Flexing dissipates energy. Over long times, dissipation damps a tumble toward a neat spin, unless jets keep re-exciting it. The surface tells on the interior, cliffs with aprons of fallen debris, pits with terraced walls, smooth ponds of fine, air-full dust where grains have resettled. If rotation speeds up enough, slopes steepen toward the angle where material gives way. Boulders might creep downslope. In extreme cases, mass shedding can occur, flecks and cobbles sliding off the equator if centrifugal force gets the upper hand over weak gravity and cohesion. That doesn't just change the shape a little, it rewrites the light curve and briefly the orbit through a tiny recoil. Temperature adds another layer. Thermal inertia, the way the surface holds or sheds heat, creates a lag between noon sunlight and afternoon warmth. Surfaces with low inertia heat and cool quickly. High inertia crusts stay warm into the evening. That lag times the thermal exhale that pushes the path. Rotate that thermal map around with the spin, and you get a repeating pattern in the non-gravitational acceleration. If observers catch the light curve and the path residuals rising and falling in sync, they can say, here is the rotation period, here is the thermal lag, here is how the push is being modulated by spin. Sometimes the spin itself seems to wander. A period measured early doesn't exactly match the period a month later. If that drift is smooth, sunlight's slow torque or sustained asymmetric outgassing is likely at work. If it jumps, an outburst probably rearranged a vent or shed a fragment. There's even room for precession, a slow wobble of the spin axis like a toy top, and nutation, a smaller nodding motion riding on top. Those motions tweak which latitudes get favoured and when, and they sneak into the light curve as slow changes in the shape of the pulse. Catching precession demands patience. You stack weeks of data, and only then does the long, slow beat emerge. All of this gets far easier and far more convincing when you layer methods. Polarimetry can show that the bright part of the pulse is dominated by fresh, fluffy dust, which means the peak isn't just geometry but also a jet. Thermal infrared can confirm that the afternoon hemisphere is contributing extra heat, right where the model says it should. Spectra can reveal that a particular gas strengthens on the same hours of the same nights, implying a vent tied to the rotation rather than random burps. When those independent threads braid together, the spin shape model stops being a guess and becomes a working map. There are bolder plays, a well-predicted star occultation when 3I Atlas briefly blocks a background star, can trace a chord across the silhouette. With observers spread along a line on Earth, multiple chords sketch a true cross-section. It's hard for an interstellar object, fast, faint, fleeting, but not impossible if the ephemeris is tight. Those chords can validate a photometric shape model in one stroke. Radar would be a dream, returning range, speed, and even rough surface texture, but the object is likely too faint and distant for that. More realistic are deep, high-resolution images that show the inner coma's structure, fans and jets that mark the vents, aligned just where the spin model predicted. Even the coma's blur carries spin information. A steady, rotating jet paints a spiral in the inner coma when viewed with enough resolution. The spacing of the spiral arms encodes the rotation period. A jet that fades and reappears in that pattern confirms that the vent is tied to a fixed spot on the nucleus, not just a transient hole in the dust mantle. If multiple jets are present, their arm sets can overlap like fingerprints. Disentangling them is tricky, but do it and you've mapped multiple active latitudes at once. Put the pieces together and you see why the chapter is more than an academic detour. Spin and shape are the steering wheel for the tiny forces that move 3i Atlas off the gravity-only line. A long body with a tilted pole warms its flanks on a schedule. Vents at particular latitudes pulse in a rhythm. Sunlight's torque edges the spin faster or slower. The thermal exhale leans not quite away from the sun, but a little forward or backward in the direction of travel. Every one of those details shows up as a small, consistent nudge in the orbit fits. Track the pulse, you track the push. Track the push, you predict the path. There's also biography in the spin. A calm, single-period rotation with a stable pole hints at long, gentle evolution, with past torques mostly averaged away. A messy tumble hints at fresher disruptions, recent outbursts, fragment shedding, or a history of close passes by other stars before it ever reached us. A bilobed shape suggests a contact binary that merged gently in its home disk, or during a slow dance sometime in interstellar space. A shard-like shape suggests a more violent past. These are not just labels, they are clues to the dynamics of another planetary nursery, written in the way a small body turns. As the campaign goes on, the model should crystallize. Early, the rotation period might come with caveats, aliases from gaps in coverage, confusion from coma light. Later, with round-the-clock coverage from different longitudes and cleaner subtraction of the halo, the period tightens to a single confident value, or to a tidy pair if tumbling is real. The pole solution starts wide, somewhere in this patch of sky, and then narrows as the amplitudes change with geometry nails down which hemisphere is summering. The shape inversion matures from long to long with a lobe here, and finally to a specific family of shapes that all produce nearly identical pulses. In the background, the physics keeps whispering the same lesson. Small forces win by being on time. A vent that breathes brightest just after local noon, every rotation will steer the path more effectively than a stronger vent that coughs randomly. A thermal lag that's the same every day will build a tidy, predictable shove into the orbit. Spin is the metronome that keeps those pushes on beat. Get the beat, and even a faint, fast interstellar traveller like 3i Atlas becomes legible. A turning, breathing object whose shape and rotation don't just decorate the story, they write it. Think of protoplanetary disks as sprawling kitchens, each with its own pantry, heat and timing. Close to a newborn star, it's blazing hot. Metals and rock condense, water can't last, and small shards collide and fuse into seeds of worlds. Farther out, the light softens, water freezes, then carbon dioxide, then even more delicate ices. Pressure bumps gather dust like snow fences on a windy plain. Pebbles drift inward and stall at these traps, piling material into rings. Somewhere out there, likely beyond the line where water turned solid, an embryo formed that would one day be whittled down to the traveller we now call 3i Atlas. It didn't stay home. Something nudged it. Perhaps a migrating giant planet. Perhaps a crowd of siblings jostling in a tight system. Perhaps a passing star in the birth cluster, and it was thrown free, a tiny ambassador launched into the galaxy. What makes that ambassador precious is the chemistry it carries. Rocks and ices are not bland. They archive temperature, radiation, and recipe. The mix of water to carbon-bearing molecules tells you how far from a star the grains first stuck. The balance of fragile ices to tougher ones tells you how quickly the young system cooled, and whether giant planets stirred the pot. The dust itself, compact like glass or fluffy like ash, remembers whether it spent ages drifting peacefully in a cold ring, or got flash-heated by shocks and UV in a rowdy, luminous nursery. Every time we split the light from 3i Atlas into a spectrum or map its colour across the coma, we're reading that archive in translation. Picture a disk where carbon-rich chemistry dominates. Grains coat themselves in dark organics, creating surfaces that absorb sunlight greedily and redden with age. Small bodies born there mature into travelers that look darker and redder in reflected light, with dust that polarizes starlight in a way that betrays fluffy, complex aggregates. Now picture a cooler, water-rich ring in a calmer, dimmer environment. Particles there gather frost, grow more reflective, and preserve extremely volatile ices close to the surface. Such a body, when it wanders inward toward another star, might wake up earlier, breathe gently but consistently, and loft surprisingly bright ice grains. Place 3i Atlas somewhere along this spectrum and you start to infer its hometown, whether it comes from a pantry rich in organics or a freezer full of delicate frost. The architecture of the home system matters too. A giant planet on a wide, eccentric path is an ejector seat. It flings small bodies into long arcs that either settle into distant belts or more often cross a line they cannot cross back and are lost to interstellar space. A pair of giants migrating through a disk can act like a conveyor belt, dragging material inward and outward, baking some pieces, deep freezing others, then scattering them wholesale. A compact system of multiple super-Earths can stir the inner disk into a frenzy, sending showers of fragments outward to mix with primitive ices. If 3i Atlas wears a hard, processed rind with fresh veins only in cracks, that hints at past baking before exile, perhaps repeated warm passes in its home system. If it wakes early with gentle, volatile-rich breath far from our sun that hints at a more sheltered upbringing. Long before we had the chance to notice it, interstellar space had its say. The space between stars isn't nothing. It is a low, relentless drizzle of radiation and tiny impacts, each one aging the topmost layers. Organic coatings darken, ice close to the surface slowly vanishes, the outermost grains sinter into a tighter crust. Cosmic rays write a quiet tattoo into the chemistry, breaking some bonds and forging others. Over millions of years, a blandly reflective surface can grow ruddy, a porous skin can harden. When 3i Atlas first pricked our detectors, it likely already wore this patina of exile, a story layered atop the story of its birth. And yet the patina is thin. Sunlight is a solvent. As the traveller approaches our star, weak seams relax and vents open. Fresh interior material stares at the light for the first time in ages. If the coma begins neutral and gradually reddens, the first breath may be dominated by clean ice grains that quickly sublimate, followed by darker, older dust that takes longer to go. If, instead, the coma starts red and stays red, interior material might have been processed already. Perhaps the body took a warm tour inside its own system before being thrown out, sealing many of its volatiles deeper than the sun can easily reach during this brief visit. Very small details point backward to the nursery. The distance from our sun where activity wakes is one clue. The sequence in which different gases appear is another. If particularly delicate gases stir at surprising distances, 3i Atlas may have unusually shallow reservoirs, implying a crust that never grew thick or a history of gentle, cold storage. If sturdier gases dominate and delicate ones stay shy, the top layers may be desiccated, worked over by heat before exile or armoured by long interstellar aging. Combine those clues with dust behaviour, a large grain's common, suggesting a crust that breaks off chunks, or a tiny grain's abundance suggesting a friable skin, and you begin to sketch a family portrait of the original disk. Spin and seasons carry biography as well, a neatly aligned spin axis, and a calm, single-period rotation whisper of a long time spent without strong torques, perhaps drifting in a wide, cold belt before the final kick. A messy tumble suggests recent rearrangement, either a violent ejection from the home system or surface changes during this very approach. If the strongest jets live in a narrow latitude band and turn on with clockwork regularity after local noon, the interior may be layered in a way that favours strong, focused vents. If activity is spotty and shifts erratically, the crust could be crackled and thin, with many small leaks rather than a few dominant sources. Those are different flavours of childhood. Disciplined assembly in an orderly ring versus a rough and tumble nursery, where collisions and migrations never let surfaces settle. Now imagine that original nursery in 3 dimensions. Discs aren't flat plates. They puff up with gas and dust, thicker in the cold outer regions. Shadows cast by inner rings can cool patches far beyond. carving cold traps where rare ices accumulate. Spiral waves can compress material in lanes, making local pockets of pressure where grains collide and stick more efficiently. If 3i Atlas carries a high fraction of fragile exotic ices that only endure in very cold niches, we might be seeing the imprint of such shadowed pockets. If, on the other hand, its chemistry is simple, with water and a few common carbon species and little else, the nursery might have been bright, warm, and well mixed, erasing those delicate zones. There's a social life to birthplaces too. Many stars form in clusters. In those first few million years, close stellar neighbours can pass within a few hundred astronomical units, near enough to yank on the skirts of one another's disks. Those flybys can shear off outer belts, seed them with foreign dust, or hurl comets outward in bulk. A traveller thrown free from such a lively neighbourhood might carry dust that looks like a blend, some grains processed by harsher radiation, others preserved from quieter corners. If the dust of 3i Atlas shows unusually mixed properties, fluffy aggregates alongside glassy shards, a mosaic of grain histories, that's a whisper of a childhood in a crowded star city. Even its size is a clue. Small bodies are both easy to eject and easy to erase by time. Larger ones are harder to eject but more likely to retain layered interiors. If 3i Atlas proves modest in size yet still rich in volatile behaviour, it could have been born in a region where pebble accretion was efficient. Small objects gathered enough mass quickly to lock in their chemistry, before migrating or colliding. If it's larger than expected for the level of activity, perhaps it spent a long time in a distant belt protected from shattering impacts, keeping its structure intact even as the outer skin aged. We also read the nursery in the way light scatters from the coma, polarization that rises steeply with viewing angle, coupled with a strong bluing during outbursts, points to delicate clumps, the kind formed by gentle sticking of icy dust in calm conditions. Polarization that stays muted with little colour, change hints at more compact grains, forged by melting and refreezing, or by repeated microcollisions that toughen surfaces. Those are the fingerprints of local turbulence and UV fire in the birth disk. A quiet disk builds lace, a rowdy one builds glass. There is a subtler map, the tempo of change. If the object's rotation period drifts over weeks in a steady way, and then steadies again, sunlight may be torquing a shape that is asymmetric but robust. Exactly what you'd expect from a body that assembled slowly and hasn't shed mass recently. If the period jolts in sudden steps, outbursts are moving mass around or revealing new vents, which can be the mark of a crust thin enough that small failures cascade, perhaps the legacy of a nursery with frequent thermal shocks. Not every clue will be legible. Some of the richest signatures, subtle isotopic ratios engraved at birth, are beyond reach without a probe to sip the gas directly. Others are simply too faint for the time we have before the traveller fades. But the beauty of a multi-pronged campaign is that many small independent hints can add up to a single, durable story. Dust colours, gas sequences, polarization curves, thermal glow, light curve beats, the measured sun-aware drift of the path. All point in the same direction when the interpretation is right. That direction, taken together, leads back to a nursery we will never see. Colder or warmer, calmer or wilder, rich in organics or heavy with ice, sculpted by giants or shepherded by super-Earths, solitary or crowded in a cluster. This is why astronomers talk about cosmic context with a quiet zeal. A tiny traveller like 3i Atlas is not just a thing, it's a sentence from a larger paragraph about how planets form across the galaxy. One sentence doesn't tell the whole plot, but it can reveal the tone, the setting, the style of the authoring disk. Pair it with the two interstellar visitors we've already read, and patterns begin to flicker into view. Add a fourth, a fifth, a 10th, and you start to compare not just objects but star systems themselves. How often disks cook up organics, how common cold traps are, how frequently giants rearrange the shelves. In practical terms, the postcard we're exporting from 3i Atlas is a packet of numbers and curves that future researchers will set beside those of other visitors. Did it wake earlier or later? Was its dust fluffier or tougher? Did its tiny non-gravitational push lean more with the afternoon warmth or more with a single stubborn vent? Those answers, prosaic line by line, are lyrical when read together. They say, here is a worldlet that learned its habits under a different sun, then crossed gulfs to show them to us, and in the light it reflects, the heat it exhales, the dust it releases, and the gentle way its path bends under forces smaller than a feather, we can still hear the nursery that raised it. Astronomers have a tidy name for the tiny extra push that makes a comet or small body wander from its gravity-only path, the non-gravitational signature. It sounds abstract, but it's really a personality trait, how a traveller responds to sunlight, heat, and internal ices that wake and breathe. With 3i Atlas, that trait is the quiet clue that turns a string of sky positions into a living behaviour. You begin with the cleanest story, sun and planets pull, object falls and flies, and then you listen for the whisper that doesn't fit. Night after night, the measured dots creep a hair off the ideal curve in a consistent way. That creep is the signature. To see it clearly, observers first make gravity do all the work. They compute a path that includes the tug from the sun and the nudges from the major planets, even the roundabout pull from the biggest asteroids if needed. Against that backdrop, they stack precise positions from many telescopes. What remains, the residuals, is the raw material of the signature. If those residuals scatter randomly, you pat yourself on the back and keep going. If they lean the same way every night, the sky's telling you there's a small, steady push tied to sunlight and surface activity. The trick is to let the model grow just enough to capture that push, without drowning the truth in details you can't justify. The simplest way to grow the model is to ask 3 questions that correspond to 3 directions in space. Is 3i Atlas being nudged slightly away from or toward the sun? Is it being pushed a little along the direction it's travelling, like a runner getting a tailwind or a headwind? Is there a tiny shove out of the orbital plane, slowly tilting the path? You don't write down formal components here, you just let the fit try small sun-aware pushes in those directions, and see which ones make tomorrow's prediction land closer to reality. The sun-facing push often wins when jets are most active at local noon. The along-track push shows up when thermal lag makes the afternoon hemisphere exhale harder. The out-of-plane push appears when vents sit at specific latitudes and refuse to balance neatly between north and south. Because activity depends on distance from the sun, the signature breathes with the orbit. Far out, cold crusts keep their secrets, and the extra push is faint. Nearer in, shallow volatile pockets warm, and the push grows. Past closest approach, things calm again. That rise and fall is the first test of honesty. If the non-gravitational term swells as sunlight swells and subsides as the light fades, you're looking at natural physics. If it spikes randomly with no matching changes in brightness or coma structure, you start hunting for bad timestamps, poor seeing, or calibration quirks. There's a rhythm inside that breath that matters just as much, the rotation of 3i Atlas. If a vent stares into the sun at a certain hour each spin, the whole body gets a tiny shove in a repeating pattern. Individually, those shoves are too small to see. Averaged over many rotations, they turn into the steady drift the orbit fit prefers. That's why teams compare the nightly residuals to the light curve. When the brightness heartbeat lines up with the subtle changes in the path, you can say with a straight face, the jet we infer from light is the jet that's steering this world by a whisper. A good signature is one you can predict. Modelers will sometimes withhold recent nights, fit the earlier data with a simple, sun-scaled push, and then ask the model to forecast where 3i Atlas will be on the withheld nights. If the object appears in the predicted search box, the signature is earning its keep. If it doesn't, you go back and ask whether you've made the push too rigid. Perhaps it should peak a little after local noon, not exactly at noon. Perhaps it grows faster with sunlight than you assumed. The point is to be guided by humility. Add only what the sky demands, keep it as simple as possible, and test the result against data you didn't use to build it. There are false signatures you learn to recognize. One is timing drift. If a camera's clock runs a bit fast or slow, positions will be systematically off along the direction of motion, impersonating a real along-track push. Another is a slightly warped plate solution, the math that translates pixels to sky, creating small directional errors. Good practice is merciless. Rotate cameras, change filters, observe the same field with different telescopes, and anchor everything to the best star catalogues. When independent pipelines, using different hardware, all recover the same gentle sun-aware push, you stop worrying about ghosts. The most elegant confirmations come from outside the numbers. If the modelled signature says there's a small push out of the orbital plane, Deep images may reveal a faint fan of dust that leans in the same direction, evidence that vents on one hemisphere are winning the tug of war. If the model says the push along the path increases after local noon, thermal infrared data can show a warmer than expected afternoon hemisphere, the exhale that gives the along-track nudge its character. If the model says the push spikes on a certain calendar date, spectra might catch fresh gas lines that also peaked then, an outburst that briefly sharpened the jets and kicked the path. Seasonality creates a symmetry in the signature that no amount of neat math can fake. A tilted spin axis gives 3i Atlas a summer and a winter. If one hemisphere wakes first and dominates, the non-gravitational term will be stronger on the inbound leg of the orbit or the outbound leg, but not the same on both. That asymmetry becomes a fingerprint. Fit a single symmetric, breathing curve, and you'll keep missing the edges. Admit the seasonal tilt and the misses shrink. It's not overfitting, it's the sky insisting that the traveller has weather. Sometimes the signature itself evolves. Early in the approach, the push may point mostly away from the sun, as shallow vents flicker to life. Later, as the afternoon side's lagged heat becomes the main actor, the net push tilts slightly along the path. Later still, if a vent chokes on its own fallen dust, a different vent can take over and the direction can swing a little again. Those swings aren't dramatic course changes, they're gentle slides you only perceive by stacking many nights. The reward for catching them is a model that keeps finding the object exactly where it claims it will be, weeks after a gravity-only ephemeris would have wandered off target. Because 3i Atlas is likely active, outgassing pushes will dominate the signature near the sun. Farther out, sunlight alone, through absorption and re-emission from a lumpy surface, continues to provide a quiet shove. Distinguishing the two in the data is possible. When the coma is thin and gas lines are absent, any remaining push is probably the thermal recoil of sunlight working on shape and spin. When gas appears and the coma swells, the push grows faster and often tilts closer to the sunline, the telltale of real jets. In practice, the model carries both behaviours, one that grows with light alone, one that wakes when ices do, and lets the data decide their mix. All of this matters for more than pride. The non-gravitational signature is the difference between pointing a telescope at empty sky and putting 3i Atlas in the middle of the frame. It's the difference between a spectrum that catches a fleeting gas line and a wasted night. It's what lets smaller observatories schedule efficiently, knowing that the prediction has accounted for breath and heat, not just gravity. And it's how you avoid embarrassing losses near twilight and perihelion, when small errors grow fangs and the object can vanish into glare if you're not honest about the extra push. Beyond logistics, the signature is science. Its strength hints at how porous the crust is and how close the ices lie to the surface. Its direction hints at the geography of vents and the lag of warmth across the day. Its change with time hints at seasons, obliquity, and whether the spin is steady or being torqued by light and jets. Compare that triad, strength, direction, evolution, against the colours, spectra, polarisation, and thermal glow, and you're no longer just fitting a curve. You're diagnosing an engine, what fuel it burns, how the pistons fire, whether it idles smooth or rough. There is one more quiet test that modelers love. After building a signature from data before closest approach, they freeze the model and let 3i Atlas swing through perihelion. If the post-perihelion positions land where the model expects, without retuning, then the physics you assumed inbound was the right physics outbound. If not, you ask what changed. Did a vent shut down? Did a slab collapse? Did spin drift enough to alter the timing of the exhale? The answer becomes a note in the object's biography. A season turned, a crust failed, a jet moved its mouth. On paper, the non-gravitational signature is just a tiny correction in a calculator. In practice, it's the footprint of breath and sunlight, of texture and tilt, printed onto the orbit of a worldlet from another star. Gravity writes the main sentence of the path. The signature is the punctuation, subtle but decisive, telling us when to pause, where to look harder, and how 3i Atlas is living its brief season under our sun. The question isn't whether we can learn from a passing interstellar traveller, it's how close we dare to get before it slips away. A full rendezvous is fantasy with current hardware. Matching speeds with something on a fast unbound path would demand more energy than our rockets can reasonably deliver on short notice. But a flyby? a carefully timed dash past the head of the coma with instruments awake and greedy. That sits right on the edge of possible. If we design for speed, simplicity and readiness long before the alert goes out that 3i Atlas is inbound. The first ingredient is time, or rather the lack of it. From discovery to best geometry could be months, not years. That means no bespoke spacecraft rolled from scratch, no meandering development cycles. You stack the deck in your favour by keeping a go-bag spacecraft on the shelf, a flight-proven bus, a compact propulsion stage, and an instrument suite already integrated and environmentally tested waiting for a target. Think of a small agile probe you could ship to a pad on a rideshare within weeks. The bus handles power, pointing, thermal and communications. The kick stage gives you the sprint off Earth. The fine propulsion, chemical for punch, electric for trim, handles the last nudges to thread the needle. Trajectory designers play a chess game against the clock. A direct escape from Earth with a high-energy upper stage gets you moving fast, but every kilogram counts. Gravity assists can help, but only if planetary alignments cooperate inside the short window a visitor grants you. More likely you accept a single, clean push to solar escape, and then shape the intercept with small course corrections informed by rapidly improving ephemerides. You aim not to catch 3i Atlas, but to cross its path at the right distance and time, slicing through the front of the coma where the gas is young and the dust is least altered. Optical navigation becomes the heartbeat in cruise. The target is faint and fuzzed by its own coma. You can't rely on a bright point-like star. The probe will take long exposures, measure a whisper of motion against background stars, and update its aim repeatedly as the ephemeris tightens from ground-based teams. Because the object's non-gravitational nudges are evolving, you plan for a string of small burns late in the approach, tiny, frequent and flexible. The goal is a controlled miss distance measured in hundreds to a few thousands of kilometers, tight enough for rich data, wide enough to avoid the densest dust jets. Instruments must be ruthless about value per gram, a narrow-angle camera to catch the nuclear silhouette and resolve inner jet structure, a wide-angle imager to map the coma and tail in context, a visible near-infrared spectrograph to read gas and dust fingerprints, water-related emission, simple carbon species, the broad slopes that betray grain chemistry, a thermal infrared mapper to weigh the warmth of the nucleus and look for hotspots that mark vents, a dust analyzer, small but hungry, to taste grains as they tap the spacecraft, measuring size and composition from impact signals, or, if budget allows, by mass spectrometry. A compact mass spectrometer to sniff the gas directly, even if only for a few breathless minutes near closest approach. Add a magnetometer and plasma package to watch the solar wind tangle with the escaping atmosphere, because that interaction shapes where dust goes and how jets evolve. Every instrument shares one obsession: duty cycle. On approach, downlink is a luxury. You're recording to solid-state memory and rationing pointing time like oxygen. The cameras bracket exposure settings in case 3i Atlas brightens suddenly. The spectrograph cycles through pre-planned lines with short integrations that can be stacked later on the ground. The dust sensor arms for high-cadence sampling during a narrow cone of time around the flyby. The avionics choreograph all of this autonomously, because light time delay turns every command from Earth into a letter that arrives after the moment has passed. Dust is the risk that never blinks. A coma is a fog of particles, from smoke to sand and beyond, each travelling on its own small arc under sunlight and gas drag. A direct run through a strong jet can pepper a thin radiator or scratch optics. Hardening helps, Whipple shields over the riskiest faces, angled panes for cameras, cable runs tucked behind structure. But the better strategy is geometry. You approach from slightly sunward where possible, skimming the coma nose rather than barreling through a tail rich in dust. You cross the plane of the most active jets quickly and at a shallow angle. Any surface that must face into hazard during the most intense minute, the dust analyzer for example, gets small and sacrificial. Even if a sprint probe never flies, we can still pull off a virtual flyby with Earth and our space telescopes. That requires choreography rather than propellant. Ground observatories watch in relay, handing off across longitudes to capture a full rotation. The best-seeing nights deliver sharp astrometry that keeps predictions honest. The mediocre nights deliver sheer volume for light curves and colour trends. A handful of space-based assets add leverage. ultraviolet spectra for gas species that Earth's air swallows, infrared measurements for the nucleus glow, and high-contrast imaging to tease out jets close to the centre, where the coma is brightest. Synchronize these watches and you can reconstruct the three-dimensional geometry of the inner coma from the changing perspectives alone. Tomography by patience. A star occultation, if you can predict one finely enough, becomes a scalpel. Spread observers along a predicted shadow path, and the silhouette of 3-Eye Atlas is carved by chords. One station sees a brief blink, another a longer one. Tie those chords together and you map a true cross-section, independent of coma. It's hard with a fast, faint interstellar target, but the payoff is profound. Size and shape pinned, not inferred. If you can catch 2 or 3 occultations at different geometries, you have a nucleus outline honest enough to test your light curve-based shape models. Radar is the tempting trump card, but physics is stingy. Unless the object comes very close, the return is a whisper below useful. Still, planners watch for a near-Earth leg or a favourable geometry with a powerful transmitter. Even a non-detection sets limits. A marginal detection gives range and relative speed that snap the ephemeris, taut and free, up precious telescope time elsewhere. Data fusion is where a virtual flyby turns into a laboratory. A polarimetric campaign tells you dust texture. Spectra tell you gas sequence. Thermal maps tell you heat flow. Light curves tell you spin. Astrometry tells you the gentle non-gravitational push. Put those on a common time axis and you get cause and effect, not just correlation. A spike in polarization and a momentary bluing of colour say, fresh, fluffy grains. If the orbit fit shows a slightly stronger sunward nudge those same nights, a vent just woke and pushed. If the thermal map shows a laggard afternoon warmth and the along-track drift grows on the same schedule, you've isolated the thermal recoil that keeps nudging the path even when gas is quiet. There's a daring middle path between pure remote sensing and a full-up flagship chase, a parked and pouncing mission. You launch a ready probe to a quiet heliocentric orbit with low demands, stable power and thermal, minimal station keeping, and you let it loiter, awake, but frugal. When a discovery like 3-Eye Atlas appears, you spend stored propellant to shape a short sprint to intercept. The loiter buys you the one thing Discovery-class targets never give: time. The penalty is that you won't pick your geometry. You'll take the encounter you can reach. The reward is that you'll have a spacecraft already in space, already checked out, already on the pad of the void. Solar sails and sunlight tricks hover at the edge of feasibility. A sail can change a probe's path steadily without propellant. Ideal for late-stage targeting when ephemerides wobble. A close solar pass, skimming low where sunlight is fierce, could in principle bend a small craft's path dramatically, the spaceflight equivalent of a slingshot dipped in flame. The price is thermal terror. New materials, new coatings, and a design that keeps the brains cold while the skin bakes. That frontier is real but unforgiving. Any concept that relies on it for this traveller must already be flying before the alert goes out. Communications are another quiet constraint. The best encounter happens when your instruments are busiest and your downlink is worst, near the sun, with antennas pointed away from Earth to keep payloads on target. You plan for big buffers and deferred gratification. The probe gulps the moment, then spends days dribbling it back across the deep space network. Meanwhile, the ground campaign continues, providing context and cross-checks that will let you interpret the flyby frames when they finally land. Why do all this when a telescope could simply watch from afar? Because a close pass lets you tie the macro to the micro. Remote spectra say, water is escaping. A mass spectrometer says, here are the precise relatives of those molecules. Polarimetry says, dust is fluffy. An impact analyzer says, and here's how big the fluff actually is, grain by grain. A light curve says, something on the afternoon side is hot and active. A thermal imager says, here is the hotspot itself, with a temperature and a size. Together they transmute the poetry of hints into the prose of properties, and we don't have to choose one path. The most powerful campaign is layered. A nimble flyby, a wall of telescopes on Earth and in orbit, and a global network of smaller instruments that can watch for weeks while the big glass is oversubscribed. Students reduce photometry at 3 a.m. Amateurs contribute deep stacks that rival professional pipelines in signal to noise. National facilities catch the lines only they can see. The probe's data, when it arrives, slots into a scaffold already built. That is how a brief minute near a stranger becomes a chapter we can actually reread and trust. There is honesty in admitting limits. A sample return from 3i Atlas is beyond reach in this visit. A rendezvous would take a breakthrough we don't yet have. But a fast flyby, designed with humility and speed, can still be transformational. An encounter that turns a faint, fast thing into a place with vents and seasons, with a crust and a breath, with numbers that plug into models of disks around other stars. And if the launch clock beats us this time, the virtual flyby remains. A symphony of light, heat, polarization, and motion, conducted across continents and orbits, that tells us nearly as much when read with care. The better we get at this choreography, shelf-ready probes, parked sprinters, rehearsed global observing plans, the less each interstellar visit feels like a once-in-a-generation miracle, and the more it feels like a program. Today the name is 3i Atlas. Tomorrow it will be another traveller with another story. The chase doesn't make the sky send them. It makes us ready when it does. There's a moment in every sky story where the numbers are still soft and the headlines go hard. A faint, fast visitor appears. A few early measurements suggest its path is shifting, and before the next observing night, the internet has filled in the blanks with everything from secret engines to doomsday arcs. Sorting signal from hype starts with a boring virtue: patience. Real signals grow stronger when you point more telescopes at them. Hype thrives in the gaps between nights. With 3i Atlas, the difference shows up in how the evidence matures, first as a hint that the gravity-only path isn't perfect, then as a consistent sun-aware nudge that survives better data, better calibration, and independent checks. Begin with images. Discovery frames are stretched to pull whispers out of noise, and that stretch can play tricks. A streak from a satellite can break into dotted pearls if the camera readout scans at just the wrong pace. A hot pixel can bloom into a phantom dot if you blink images too fast. Pipelines fight back by subtracting reference skies, rejecting known bad pixels, and demanding that a candidate move in a straight, sensible way over multiple exposures. Even so, every tracklet, those link detections over minutes, gets human eyes before anyone claims it's the traveller. Experienced observers look for telltale lies, a would-be object that aligns suspiciously with a sensor artifact, motion too tidy to be real, a signal that sharpens when you shift stack along the predicted path and vanishes when you offset slightly. Hype points to the one frame where the dot looks dramatic. Signal points to the stack where the dot still exists when you change the recipe. Astrometry, the precise positions on the sky, is where hype most often stumbles. A small error in a camera's clock can nudge every point along the direction of motion, masquerading as a real physical push. A slightly warped plate solution can tug points sideways, hinting at a fake out-of-plane force. The antidote is redundancy. Teams reduce the same night's images with different software, anchor to the most accurate star catalogues, and rotate instruments and filters to make sure no quirky setup is fooling anyone. When the small nightly differences between prediction and reality line up in the same direction across multiple telescopes, the case strengthens. Hype hates multiple instruments, Signal needs them. Preprints and press releases arrive faster than peer review, so they need careful reading. A responsible preprint tells you exactly how many nights of data the conclusion rests on, how big the uncertainties are and what assumptions went into the model, especially whether non-gravitational pushes tied to sunlight were allowed. It will show residual plots, not just smoothed curves. It will describe which data points were rejected and why. It will offer the ephemeris so others can test it immediately. Hype leans on dramatic before/after graphics and treats uncertainty as an optional footnote. Signal treats uncertainty as the main character. The shrinking boxes on tomorrow's sky map. The quietly improving we know where to look. Words matter. Shifting can sound like a swerve. In the data, it's a consistent handful of arcseconds over many nights. A steady lean that grows and fades with sunlight and rotation. Good communicators translate without inflating. Sunlight pushes a little. Heat re-emitted from a warm afternoon hemisphere pushes a little. Any gas escaping through vents pushes a little. Add those gentle nudges for weeks and you get a path that needs a tiny correction beyond gravity. Hype takes that correction and smears it across the imagination. engines, evasive action, omens. This is where checklists help. Is the nudge sun-aware? Does it strengthen as Three-Eye Atlas brightens and weaken as it fades? Do spectral hints of gas or a slight coma appear when the push is strongest? Do independent reductions agree on the direction? If you can answer yes, you're in the realm of signal. Light curves, the rise and fall of brightness as the object rotates, are another target for overinterpretation. A lopsided shape can make brightness swing. Patchy surface reflectivity can too, so can a jet that adds extra light when it faces us. Hype is eager to assign a dramatic meaning to every wiggle. Signal watches for repetition. If a bump recurs every rotation and lines up with a small change in the orbit fit at the same local times, event is probably involved. If the bump slides, vanishes, then reappears with a new phase as viewing geometry changes, shape and surface albedo are likely to blame. Either way, the light curve gets read next to spectra, polarimetry and thermal measurements. Lone graphs invite stories, layered graphs constrain them. Spectra are the most abused when hype wants a headline. A faint glow at the position of a known gas line can be tempting to announce. The careful habit is to verify. You subtract the signature of a sun-like star observed the same night to remove the solar fingerprint from reflected light. You check that Earth's own atmospheric glow isn't being misread as the comet's. You bin the data differently, change extraction apertures, and confirm the feature persists. You see whether that hint of gas strengthens on multiple nights as Three-Eye Atlas warms. If the line fades when it should rise with sunlight, the safer interpretation is not yet, or too faint to trust. Hype calls a first glimpse a discovery. Signal calls 3 independent glimpses with a matching rise in dust or drift, a detection. Images of the coma and tail seem self-explanatory. Look, a plume. But even here illusions lurk. Aggressive processing can imprint false fans. Background galaxies can masquerade as tail knots if the tracking smears stars and leaves extended sources behind. Experienced teams publish both the pretty, stretched version and the raw, lightly processed one. They'll rotate the field, switch filters, and show that a feature rotates with the nucleus rather than staying tied to the sky. They'll warn when moonlight or thin clouds elevated the background so much that faint structures are untrustworthy. Hype loves a single dramatic frame. Signal survives changes in method. Modelling choices are a quiet battleground. A gravity-only orbit is simple but incomplete when an object is breathing. A model with dozens of free parameters can fit anything and explain nothing. The honest path starts with the fewest additions, one small push related to sunlight, allowed to grow as the object nears the sun, and asks whether that alone reduces residuals in a way that continues to hold as new nights arrive. If the fit only improves when you add vents here and here, a tilt like this, a thermal lag like that, each tuned to perfection, you've built a story that might be too specific for the data. Hype enjoys ornate models. Signal prefers humility and predictive power, like, we withheld last week's data, and the simple model still put Three-Eye Atlas in the search box. Social media accelerates speculation, so a parallel effort has to accelerate context. Short, clear notes that say what changed and what didn't. 2 new nights, residuals still lean sunward, no new gas lines detected, light curve period now agrees across 3 longitudes. Do more to cool hype than scolding. Sharing finder charts, posting ephemerides, and inviting amateurs into the hunt turns rumour into participation. If a claim starts to spread, it just sped up. The fastest fix is a plot from multiple teams showing the same steady drift or the same unchanged spin. Openness isn't a press strategy, it's quality control in public. Then there's pareidolia, the human habit of seeing faces in noise. Stack 10 images and a faint arc appears. The mind reads structure, the heart reads craft. The cure is angles and time. Does the arc stay aligned with the sun as geometry changes? Does it move with the nucleus, not with the field? Does it appear when you leave out one of the frames? Signal passes those tests. Noise fails at least one. Uncertainty communication isn't hand-waving, it's the plot. Those little bars on a point, the pale cone on a future sky position. They are promises about what you do and don't know. Watching them shrink night by night is the satisfaction of honest work. Hype sees uncertainty as an invitation to invent. Signal treats it as the frame around the picture. When you hear, we're 60% confident it will be here, 30% there, that's not weakness. It's the map you use to schedule telescopes and decide where to look first. The press cycle is its own physics. A first look lures eyeballs, corrections sink quietly. Teams plan for this by writing their own plain language abstracts before the rush. What's been measured, what hasn't, what would change the story, what definitely won't. For 3i Atlas, that means repeating simple guardrails. Not on a collision course, no sign of control. Drift consistent with sunlight, heat and outgassing. Next checks a spectra at such and such dates, deeper polarimetry at these phase angles, and astrometry throughout. A specific watch list channels curiosity into more measurements instead of more mythology. Reversals happen, and they're not scandals. A vent shuts, a slab collapses, a dust storm on Earth ruins a key night, a clock offset is discovered and fixed, a line thought to be real fades under better data. Hype turns that into, they were wrong. Signal calls it what it is, the model catching up with a changing object and better calibration. The right question after a correction isn't, were you wrong before? But, what do we now understand that we didn't? If the ephemeris tightened, if the rotation period settled, if the coma's colour trend became clear, then the story moved forward. Finally, the most important filter is comparative thinking. Lay today's claims next to what we learned from other interstellar visitors and from hundreds of solar system comets. If a claim says 3i Atlas is doing something unprecedented, the burden of proof rises. Unprecedented isn't a ban, it's a budget. Show multiple instruments, independent reductions, repeated detections, and a physical explanation that doesn't require magic. If, instead, the behaviour slots neatly into patterns we recognise, gentle, non-gravitational drift tied to sunlight, light curves that reveal spin and shape, dust tails that sort grains by size, then the extraordinary thing isn't the mechanism, it's the origin story, that these familiar processes are playing out on a world built under another star. So the practice for anyone following along is simple and strong. Look for repetition across nights, look for agreement across instruments, look for explanations that get tested by withholding data and predicting the next frame. Look for teams who publish ephemerides and invite checks, not just graphics. Look for language that puts uncertainty up front and still offers something to watch next. Do that, and what remains of 3i Atlas after the fog burns off is better than any hype. A careful, readable record of how sunlight, heat, and ice nudge a traveller from elsewhere, mapped in dots and curves, not in headlines. What to watch next begins with geometry. As the angle between the Sun, Earth, and the traveller changes, different truths come into focus. Low phase angles favour seeing the nucleus cleanly. Higher angles exaggerate the texture of dust and make polarization measurements sing. The schedule writes itself. Catch a sweep of colours and polarization, while the phase angle climbs, repeat it on the way down, and look for the telltale signature of fresh grains, early that gives way to processed dust later. If the colour slope flattens as the coma strengthens, small bright ice grains are likely taking the stage. If it reddens steadily, darker organics are asserting themselves. Each repetition filters coincidence into trend. Keep one eye on the orbit fit every time new astrometry lands. A small sun-aware push should grow toward closest approach to the Sun and soften after. Any steady rotation of that push hints at seasons or shifting dominance between vents. If the along track component swells just after local afternoon on the nucleus, thermal recoil is doing quiet, reliable work. If the push leans more sunward when the coma brightens, jets are carrying the load. The story is in the residual plots. Scatter that refuses to pick a side is noise. A soft, consistent lean is character. Rotation will continue to reveal itself if we let it. String together light curves from multiple longitudes so there are no gaps a fake period can hide in. Watch the amplitude as the viewing geometry changes. A growing amplitude argues for a long, lumpy shape. A shrinking one can mean we're looking more end-on. If a beat pattern emerges, two close-by periods interfering, you may be seeing a slow tumble. Track whether the period drifts over weeks. A smooth drift points to sunlight's torque, or persistent asymmetric jets, while a step change points to an outburst, a slab collapse, or a fragment shedding event that rebalanced mass. Spectroscopy deserves cadence, not just depth. Early, integrate longer to chase delicate gases that wake far from the sun. Mid-approach, shorten exposures to track line strengths across a full rotation. Late, return to long integrations to catch late bloomers or to set firm upper limits. Pair visible and near-infrared with whatever ultraviolet or thermal coverage you can get. If a gas line crests an hour or two after the light curve peak, that lag is a fingerprint of heat sinking into shallow layers before venting. If lines flare at the same rotational phase for several nights, you've pegged a vent to a place on the nucleus, even without seeing the surface. The coma will write in its own handwriting. Close to the nucleus, look for narrow fans that rotate with the light curve. Farther out, look for layered streamers that betray grain sizes and launch times. Process the same images gently and aggressively and show both. Features that survive restraint are the ones to trust. Track how far heavy grains hang around before peeling into the tail. If they linger, vents are lifting big pieces and the crust may be tough. If everything goes wispy quickly, the skin may be friable and fine. A sudden symmetric halo that swells and fades over a day is an outburst. A one-sided rotating fan is a routine breath-given shape. Polarimetry earns its keep when phase angles are changing quickly. Map polarization against phase on the inbound leg and again outbound. Where the curve peaks and how high it climbs points to grain porosity. If the peak shifts after a major brightening, the dust mix changed. Fresh fluffy aggregates briefly dominated, then compact grains returned. Combine that with color changes and you'll have a 3-point check. Bluing plus higher polarization equals fragile, young grains. Reddening plus lower polarization equals older, compact dust that has been tumbled and toasted. Thermal infrared is the quiet partner that tells you size and temperament. As reflected light rises and falls with geometry, the nucleus's heat changes more sedately. Fit both together to separate how big from how shiny. Revisit the thermal light curve as often as possible. If its peaks arrive consistently after the optical peaks, that lag is your measure of thermal inertia. A small lag means a fluffy, insulating skin. A large one means a tighter, rockier crust. If a hot spot appears and tracks the rotation, a vent is bearing a warm throat. If the whole afternoon side glows broadly, thermal recoil is doing the heavy lifting, even when gas is quiet. Expect the non-gravitational signature to evolve with the season on the nucleus. If one hemisphere takes a summer, the push should be stronger inbound or outbound, but not both. Build that asymmetry into the model only when the data demand it. Premature complexity is a trap. A good test is to fit inbound, predict outbound without retuning, and see how honest your forecast was. If predictions fail right after a photometric outburst or a change in the light curve, assume the object changed, not that gravity forgot its job. Watch for fragments, but don't promise them. If the light curve suddenly smooths or the amplitude drops, mass may have slid toward the equator during a mild spin-up. Deep stacks might reveal faint companions drifting along nearly the same path. If they exist, they'll be brightest soon after birth, and then fade ruthlessly. Fragments give priceless cross-checks. Their shared non-gravitational drift will confirm that sunlight and jets push the family the same way, and any slight divergence will expose subtle differences in surface activity and spin. Occultations are worth the work. Scour the star catalogues for close shaves and publish predictions early, with uncertainty tracks so observers can line roads with portable gear. Even one clean chord across the silhouette pins a true dimension. A handful of chords maps a cross-section that either blesses or corrects your shape model from light curves. If the occultation is grazing, a wavy light curve can reveal a ragged limb. Cliffs and pits by proxy, turning a fast blink into topography. A modest radar chance, should geometry and brightness ever cooperate, would snap the ephemeris taut and hint at surface roughness, but plan as if it won't happen. The traveller is faint and fast. Most of your truth will come from photons, not radio echoes. If a radar window opens, take it. Then fold those ranges and velocities back into the orbit solution, so the whole campaign wastes less time hunting. Amateurs and small telescopes widen time more than aperture does. What they lack in collecting area, they repay in cadence and geography. A dozen well-calibrated backyard rigs can stitch a rotation that a single 8-meter telescope hopping targets between scheduled programs might miss. Publish finder charts and exposure recipes that match the object's current motion and brightness. Ask for unfiltered or broadband photometry when color is stable, and for specific filters during coordinated color and polarization nights. Every accepted frame should return a clock check and a plate solution sanity check. Good housekeeping is where tomorrow's predictions are saved. Pre-covery hunts continue to pay. With a stable orbit and a reasonable model for the subtle push from sunlight and gas, track and stack through survey archives to add nights before discovery. 2 faint dots from a week earlier can do more to collapse uncertainty cones than 10 decent measurements tonight. Those backfilled points will also tell you if activity started earlier than anyone noticed, if a shy coma was already present when the object was dim, or if everything truly woke in view. Plan for twilight. The hardest nights, when glare from the sun eats dynamic range and the atmosphere wobbles, are also the nights when geometry changes fastest and leverage on the orbit is strongest. Non-sidereal tracking helps keep the nucleus sharp. Stacking many short exposures tames the glitter. If you miss these windows, your post-perihelion ephemeris will carry avoidable scar tissue. If you catch them, predictions weeks later will feel effortless. Set a practical watch list and keep it public. Where does the light curve peak fall relative to the small nightly shifts in position? Are polarization and color moving together or in opposition? Does the along track push grow with the afternoon thermal lag you measure in the infrared? Are gas lines rising or flat when the coma brightens? Does the orbit model that fit inbound also land outbound within the advertised uncertainty? Each yes turns speculation into structure. Meteoroid stream forecasts are a long shot but cheap to compute. If dust release is strong and the orbit crosses Earth's path at some future date, note the calendar with caution. The answer is usually too diffuse, too faint, but when streams exist they are quiet confirmations that dust really left where and when you thought it did. A whisper of meteors years from now is a postscript worth writing down today. Expect the traveller to change and design your routines around that fact. An event that dominates in 1 week can choke under its own fallout the next. A smooth, single-period rotation can sprout beats as sunlight torques the shape. A coma you could not separate from the nucleus can suddenly bloom, forcing different extraction apertures and new photometric strategies. Build flexibility into scripts and vigilance into reductions. The sky won't issue a memo before it edits the subject. As data accumulates, start the meta-analysis you will wish you had begun earlier. Archive spectra with uniform calibration, so line ratios are comparable across nights and instruments. Store light curves with absolute timing discipline and clear flags for clouds, moon and seeing. Keep polarization angles and degrees tied to the same reference so inbound and outbound curves overlay without contortions. Today's clean bookkeeping is next month's discovery when someone notices a small but persistent asymmetry you were too busy to see live. Comparisons will sharpen meaning. Lay the dust colours, gas sequences, polarization peaks, and the behaviour of the non-gravitational push beside those of other interstellar visitors and of well-studied comets from our own deep freeze. If 3i Atlas lands squarely in familiar clusters, universality is the headline. If it sits off by itself, earlier wake-ups, weaker waterlines, stronger far-out volatiles, then Earth environments across the galaxy are more diverse than our 2 previous samples suggested. Neither outcome is a defeat. Both are maps. There will be temptations to overfit as the object fades. Resist them. When signal-to-noise drops, your imagination grows louder. Let models contract, not swell. Keep the simplest version that continues to predict positions honestly, and that threads the last spectra and light curves without heroic assumptions. The cleanest legacy you can leave is a set of measurements and a modest model that future travellers can be compared against without apology. Communication remains part of the work. Short, unglamorous updates that say, 2 new nights, residuals still sun-aware, rotation period unchanged within error, no new gas lines, polarization up a notch at higher phase. Diffuse rumour and invite contribution. Share failures. Twilight beat us here. Clouds ate the infrared. This line was airglow all along. The trust you bank today pays for coordination tomorrow when a rare occultation path needs volunteers or a hard twilight run needs extra eyes. When the object finally slips below the reach of casual instruments, the watch doesn't end so much as thin. Large telescopes will carry the last weeks. Small ones will chase longer integrations to squeeze out a few more rotations. The ephemeris files get shorter, the uncertainty cones grow again. This is the moment to run the fit inbound, test outbound exercise one last time, and to write down plainly where the model won and where it didn't. The last frame should be treated with as much care as the first. They will anchor the outbound asymmetry every future paper will cite. What remains on the docket after the lights dim is a series of specific testable threads. Whether the inbound and outbound dust mix truly differed, whether a single vent dominated or the torch passed, whether thermal recoil alone can explain the late drift, whether the spin changed measurably under sunlight's torque, whether the size and albedo settled to a narrow range when all datasets were fused, whether any fragment ever showed its face, whether a humble occultation ever gave us a true width. Each thread can be tied now or left for patient hands, but all of them point to the same horizon, using the quiet details of one visitor to make the next one legible faster, with fewer wrong turns and with more of the sky invited into the work. 3i Atlas will not loop back for a second act. The next you watch is not its return, but our readiness. The best sign you'll see that readiness growing is boring. Smaller prediction boxes, steadier periods, cleaner residual plots, and a public ledger that turns rumour into rows and columns. Keep watching those and you will know, day by day, whether we are truly learning from this fleeting season of light. And that's where we'll leave tonight's journey, on a quiet note of wonder, with a traveller threading the dark and our curiosity wide awake. 3i Atlas is already shrinking back into the vastness, but its faint push against the grain of gravity has carved a place in our minds. We came looking for drama and found something better. Patience turning into proof, tiny forces adding up, and a community of eyes catching a whisper in the noise and calling it by its true name. In a way, this story was never only about 3i Atlas, it was about how we learn, how careful measurements beat loud guesses, how the smallest mismatches can carry the biggest meanings, how a map drawn in pencil becomes clean ink as more hands hold the ruler. It was about sunlight behaving like a breeze, heat like a sigh, and ice like a memory that wakes when the light returns. It was about rotation setting the rhythm and dust writing the lyrics across the sky. It was about admitting what we don't know yet and loving the chase anyway. 3i Atlas arrived as a point of light, became a question, and then, slowly, stubbornly, turned into answers you could stack. A light curve that spoke of shape and spin, a soft halo that hinted at breath, a path that leaned just a little toward what physics said it should when a small world warms. Not a swerve, not a secret signal, not a warning, just the ordinary, extraordinary truth that even a speck can leave a trace you can measure from millions of kilometers away. If you felt your sense of scale shift tonight, keep that feeling. The same sky that holds galaxies also hosts this single, fleeting visitor, and both can teach. If you felt your faith in patient science get stronger, hold on to that too. The universe doesn't owe us clarity, it offers us patterns, and we earn clarity by returning night after night until the pattern stands up and introduces itself. So tell me, what do you think this traveller will leave behind with you? Is it the idea that sunlight can steer a stone? The image of a nucleus breathing through cracks like a sleeping thing that stirs at dawn? The thought that somewhere around another star dust and ice followed a recipe we're only now beginning to taste? Drop your answer in the comments. I read them all, and I'd love to hear which part of this mystery hit home for you. If you found value in this deep dive, help this little corner of the internet grow. Like the video so the algorithm knows this kind of slow, careful storytelling matters. Subscribe if you haven't. This channel lives on curiosity, and tap the bell so you don't miss the next chapter in our tour of the strange and the beautiful. Share this with a friend who always looks up, or with the person who insists space is just empty. Show them that emptiness has texture, and that texture has a story. To the observers who chased the dots, the amateurs who stacked sleepless hours into Signal, and the teams who posted ephemerides and opened their data, thank you. You make the night feel smaller and the world feel kinder. To the skeptics who kept the hype honest, you're part of the engine too. Science is a conversation, and the best parts of it sound exactly like this. Show me, check me, try again. 3i Atlas will keep going, and so will we. We'll keep returning to the same questions with better tools and steadier hands. We'll keep trading wonder for understanding and finding somehow that wonder grows back larger every time. Before you go, step outside if you can. Let your eyes dark adapt for a minute. Find a quiet star and imagine that somewhere far beyond it, a small body is beginning a long, cold journey that may one day cross our path. Imagine the instruments being tuned, the calendars getting marked, the first faint detection that turns into a night like this. If you're new here, you're welcome. If you've been travelling with this channel for a while, you already know our promise. No shortcuts, no cheap mysteries, just the careful joy of learning. Next time, we'll pick up another thread. Maybe a world with an atmosphere that shouldn't exist. Maybe a myth that crumbles under the telescope and becomes something truer. Maybe a problem so old it feels new again. Whatever it is, bring your questions, bring your patience, bring that stubborn curiosity that refuses to quit when the graph looks noisy. For now, thank you for spending your time and your attention on a story that asks you to slow down. The universe rewards that kind of attention. It always has. Good night, clear skies, and until we meet again under the same broad dark, keep looking up.